Hello everyone, and welcome to this video on section 2.2 called Determining Volumes by Slicing, and this section specifically on the disk and washer methods. So in this video, I'm going to be taking you through a sample version of a Newton Alta assignment for this section. So here's what your homework page will look like. Top of it, you have the title of the assignment. You won't see the word preview. Upper right corner, you got your mastery bar telling you how far along you've gotten, and your activity bar telling you how far you've gotten in each objective. So it looks like there are, 5 objectives here in this assignment, and each objective has their own, progress circle. And then you have a question about a certain objective, right? So the current objective is, determine the volume of a solid by integrating a cross section. And at the bottom of every question, you should be seeing a feedback button where, if you're seeing a typographical error in the problem or something's wrong with it in some way, you can send feedback directly to Newton. They can help you. You will not see this instructor cheat button, right? This will not be there. I'm in teacher mode right now, so that's not going to be there for you. You will see this more instruction button. So if you're ever struggling on a particular objective, click on this, go to the more instruction area, and you'll be given some reading to do or some videos to watch or both. And then they'll give you some problems to do, while the instruction is still up on screen. So you can keep referring back to it, and maybe that'll help you get through the assignment as well. All right, so now to this first question. Oh, one more thing, my apologies. Please understand that the questions I see in this video may not be the same questions you see, same exact problems you see when you work on the assignment yourself. But, they should be similar enough to where watching me do it here help you when you're doing it on your own. All right, so here we're asked to determine the volume of a solid, a three-dimensional solid figure, by integrating a cross section. This first question, find the volume of the solid whose base is in the first and second quadrants on the XY plane. So we're going to be drawing a region on the XY plane, and this region will be the base of some three-dimensional figure. So bounded by y equals 16 minus 4x squared and the x-axis, using square cross sections perpendicular to the x-axis. And then enter answer using exact values. So they want the volume here in cubic units. So let's go to some paper here and draw this region out. So the region in question, let me grab a thicker marker. So the region in question was under the curve. They said y equals 16 minus 4x squared. And just the first and second quadrant, so everything above the x-axis. So the graph of that curve, right, you'd have 0, 16 as the y-intercept, and it would have x-intercepts of, and this isn't perfectly to scale or anything, but 2, 0, and negative 2, 0, right? That's where it would hit the x-axis. And it's a parabola, opening downward with the vertex at 0, 16, right? So and they're going just to the x-axis, they said, right? Bounded below by the x-axis. So we're talking about this region. All right, so this region is the base of some three-dimensional figure, right? So I'm gonna shade this region here. Right? Again, they're saying to us that this is the base of a 3D solid. Right now I'm in 2D, but so imagine there's something popping out of the screen at you. You know, but when you look at it from a bird's eye view, right, from above, you see this shape. There's something coming out here. There's a three-dimensional figure. And then they further told us that there are square cross sections perpendicular to the x-axis. So here's the x-axis, right, left and right. So that means when I cut, if I were to slice straight down, perpendicular to the x-axis, so I make a little slice here. And what I'm going to do is I'm going to envision this slice as a thin rectangle, very, very, very thin rectangle. All right, so here's a slice that's, perpendicular to the x-axis. We'll call the thickness of this slice, and I'll do it above, let's say the middle of the slice here is at a value called x, um, maybe xi. All right. And the thickness, the thickness of the slice I'll call delta x. Now, if I were to pull the part I cut off away and then look at it from the side on the right here, I'd see a square, right? They tell us that there are square cross sections. So really, what I want to do is just pull this slice out. Right? So I pull this slice out of the 3D figure, and it would look like this. You'd have this thin rectangular base. It would be really thin rectangular base like this, where again the thickness I called it delta x, and they told us there are squares popping out of this, right? Squares heading toward your screen here, right? So this, maybe I'll do it the other way. So there's a square popping out at you. So when I pull this slice out, right, it should look something like this. Again, this is a nice square cross section. And I should be able to do this, right, for any value of x. I guess I could have just called this x instead of xi, but I should be able to do this for any value of x from, -2 to 2. Now, what I'm going to do now is take this little thin section I cut out here. We're going to find the volume of this, and then I would do that for every x value, from -2 to 2, add them up. So this will, the sum of all those, and we're going to have, delta x go to 0, so that'll become dx, right, the differential of x. So when I do this, for every x value between -2 and 2, we'll be integrating, right? I'd be add up all these slices, right? Add up the volume of each slice. All right, so what I want to do now is find what's the volume of just one slice, right? So at this x value here, I cut out that slice with this thickness, a little tiny delta x. Again, I'm going to say we're going to change that to dx soon. So I'll just call it dx from now on, or dy if we have delta y. And I want the volume of the slice. So let's say we want volume of a slice, and then we'll add up all the slices, all the volumes of the slices. So that'll be this. So the volume of a slice, I'll label it as V slice like this. Well, it's simply a square base, right? You have a square and then another square, connected by these little thin walls. This is actually a rectangular prism or a square prism. So remember, the volume of a prism is the area of the base times the thickness, times the height. So I need the area of this square. Now, they might write this in general as, you'll see this in some texts as, since I'm doing dx here, delta x, I'm going to find the area of this base in terms of x. So you see this function a of x times the thickness, times delta x, which again we'll write as dx later when we add them all up and integrate. Here's the area of a cross section, which in this case is a square. Area of this square cross section, the base of this thin slice. And I want things in terms of x. Well, if it's a square, then, the height of the little rectangle I cut up here, that's this, right? What I drew up here, that's this. And if it's a square, every single one of these sides should be that length, right? All four sides are the same. And for this particular x value, for any x value I choose, the length of this rectangle here is the y coordinate, right? The y coordinate here of the top, to the top of the slice from 0 to y. But what is the y coordinate in terms of x? Well, I'm on this curve. The y coordinate in terms of x is 16 minus 4x squared. All right, so this is 16 minus 4x squared for the length of this rectangle. So that's the length of one side of the square in my picture of the slice. And so it would also be the height of it, right? It's a square. Same thing all around. And the area of a square is just, your side length squared, right? So the volume of this slice, right? The volume of this slice is the area of my square, my cross section, right? The area of the square there, 16 minus 4x squared, right? It'd be 16 minus 4x squared times 16 minus 4x squared. And then times delta x, right? There's the volume of one slice. Well, we're going to do this for every single value of x from -2 to 2 and add them up. And again, we'll have them be super thin. So I'll call this, dx, the differential of x, right? Delta x approaching 0. Call it dx. So the total volume, I do this slicing for every value. The total volume of the three-dimensional solid they're talking about going to be an integral. Right. Integral is adding up a bunch of things, right? It's just adding things that are like infinitely thin, right? Infinitesimally thin. Again, I said I'd be doing this for every x value from -2, +2. And for every single x value, I get a slice looking like this with a square base and the volume of the thing we're adding up, right? We're adding up all these here, all these slices, these slice volumes. 16 minus 4x squared, and then again, delta x here becomes dx, right? We have delta x approach 0, becoming, dx, right? All right, and now I'm just integrating this. Okay. So one thing I'm noticing that can simplify this a tad, do you see the symmetry? See how the area in the first quadrant for the base here is the same as this region it's just the same area, reflected across the y-axis, right? This graph is even, and so is this function here, right? If I take this a of x, right? This was the a of x, the area of a cross section. This is an even function. Remember, so a of -x would be the same as a of x, right? And you might recall from maybe a previous calculus, right? Calculus 1, that if you have an even function, I can just take from, instead of doing -2 to 2, I can do the volume from 0 to 2 and then just double it. So I'm going to do that, right? So we're going to double the area, or the volume, sorry, the volume from x equals 0 to 2, right? Just cutting this in half. I think that'll make things a little easier. I mean, I think it's easy already, but there's only going to be a polynomial here. But having 0 as one of the limits will also simplify things even more. Right, so we're doubling, the volume on the right, and that'll give us the whole thing because of this symmetry. All right, so this I got to multiply out. Now I'm actually going to factor a 4 out of this. So then we'd have 4 times, 4 minus x squared. 4 is being squared, that'll be 16. So I'll pull the 16 out. 3 times 16 is 32. Okay, again, that's just factoring 4 out of this quadratic here, and then remember that it's being squared. And then what we have is 4 minus x squared in here, dx, and we're going the integral from 0 to 2. Need to multiply this out, right? I can't integrate this product. Gotta sum, so it's 32 times the integral from 0 to 2 of, and then when I multiply this out here, this would be 16 minus 8x squared plus x to the 4th with respect to x, right, times the little thickness of the slices dx. And now I can integrate. This will be 32. Take the antiderivative of this without the constant of integration, right? Without that plus c. So that's 16x minus 8/3 x cubed plus 1/5 to the 5th. We're evaluating this, going from x equals 0 to x equals 2. And you see that, when x equals 0, this is all 0. Right? So that's kind of why I did the symmetry thing earlier. So I'm just going to plug in 2 here, right? You plug in 2, you plug in 0, and then you subtract the results. I'd be subtracting 0. So this is really just what you get when you plug in 2. So this would be 32 times, and then 16 times 2 is another 32, minus, and then 2 cubed is 8. So you have 64/3, and then plus 2 to the 5th is 32. So plus 32/5. Okay, and then we'll get this as a single fraction. You could distribute the 32, or something else I would rather say is, hey, look at all these would have 32 as a common factor. So I could pull that out, get 32 squared out here. And then times, 1 minus, and then 64 is 32 times 2, so that's 2/3. So that's 1/3. And plus and 32 times 1/5, right? Just a 1/5 come from that. This is 1/3 plus 1/5, right? That'd be 8/15. All right, this is 8/15. 1/3 plus 1/5. And then 32 is 2 to the 5th. So this is 2 to the 10th times 2 to the 3rd is 8. This is 2 to the 13th power. So this total volume here is 2 to the 13th power over 15, right, cubic units. And you know what? I'm going to type that in. Well, actually, now we can do this. 2 to the 10th power is 1024, and then 1024 times 8, that'd be 8,000 plus 160 plus 32, so 8,000. So that's 8,192 2 to the 13th power, that's 2 to the 10th times 2 to the 3rd. 1024 times 8. Divided by 15 cubic units. All right, so I'll write this in. Again, it's a volume, cubic units. Now let's go back and enter that value. So 8,192 divided by 15 cubic units. Wait. Now I'm pretty sure that you could have entered 2 to the 13th power divided by 15. I think most of these Newton-Alta problems, if you enter a value that's equivalent to the value in question, it'll give it to you. So maybe I'll check that out for future problems. All right, so you see the progress bar bumped up a tad. It starts off slow, but the more you do correct in a row, it'll fill up faster. It should be complete in 4 to 5 questions. All right, and then after every question, right there, see they're trying to show you the 3D figure here. It's a little ugly, but and then a slice, right? Remember that little square prism thin slice I had a picture of on my paper. I got that in orange here. Yeah, after oh yeah, you can zoom. Oh, okay, this might not be bad. Move graph. Yeah, so here's the 3D figure that they're talking about. All right, where they took that region and have square cross sections perpendicular to the x-axis. Anyway, so after every question, there's going to be some sort of answer explanation. Please read these, and whether you get it right or wrong. If you get it right, read through it just to see if they did it some way you like better, and then you'll try for future problems. Obviously, if you got it wrong, it'd be beneficial to read through just to see, where you went wrong or what you could have done better. So next question. All right, so we're in the same objective. So that, taking a thin slice out of the figure, finding the volume of that slice, and then integrating over some interval to find the total volume. All right, so this is find the volume of the solid whose base is a circle with a radius of 6, right, and has cross sections perpendicular to the x-axis that are squares again. Rest of the exact values once more. Okay, so back to my paper. Let's write this out. All right, so they said the base, again, the base is some two-dimensional figure on the XY plane. And they said it's a circle with a radius of 6. I'm assuming, well, I mean, we can just put this anywhere we want. So I'll put it so that it has a center at the origin. So there's 0, 6. Here's, 6, 0, 0, -6, and -6, 0. All right, so here, a very, very rough sketch of a circle. This isn't a great circle, but so here's a circular base. All right, and again, you got to imagine some 3D figure popping out at you with this base. And we're making slices, perpendicular to the x-axis again. So here's the base. I'm just going to kind of shade it in. There's the base of this 3D figure. And we're making slices perpendicular to the x-axis once again. All right, so once again, here's a slice, right? So I go to some x value here from, -6 to 6 and make a thin slice, right? So again, I'll think about this as some thin little rectangle. Right, here's a slice. Now the slice, we'll call the thickness this time. I'm just going to call it straight up, dx, right? It's a tiny little horizontal change of area, and that'll shrink to nothing when we integrate the limit. So I'm just going to call the thicknesses the differential of x, differential of y from now on. And if I were to pull that slice out, right? If I were to remove the slice and look at it on its own, right? Again, it's just some thin rectangle on the bottom and the top. Some thin rectangle. But it's once again, they said square cross sections. So the face of it is another square. Okay, so this isn't great, but this is another square. Square face. A very thin rectangular slice. So again, the thickness I'll call dx, right? Delta x dx. And what I want now is to find the area of the face, right? The area of the face times the thickness gives me the volume of this slice. So again, the volume of the slice, I'll call V slice, is area of the face, right? Which I want in terms of x. That's why I'm calling it, A of x times dx times the thickness dx. Again, I called this delta x in the last problem. As the area of the square face, area of the cross section, times, the thickness. And then we're going to integrate from, we're going to do this for every x value from -6 to +6. Okay, now, just like last example, right, I would like to get this length of the slice here, right, which would be this here on my picture of just the slice. I'd like to get this in terms of x. Right. All right, so that's where the equation of a circle is going to come in, right? A circular base, a circle with a radius of 6 would have this equation, and centered at the origin would have this equation, x squared plus y squared equals 36, right? That's 6 squared. That's the equation of our circle. The top half, if I were to solve for y, the top half would be y equals the positive square root of 36 minus x squared. There's any positive y coordinates up there. And the bottom half, right, the bottom half of the circle would have the equation y equals, negative square root of 36 minus x squared, right? If I were to take my equation for the circle and solve for y, you get two possibilities, right? One for the top half of the circle, one for the bottom half. So this distance here, right, just from the x-axis to the top, that's the y coordinate of that point on the curve. But if I want it in terms of x, right, that's square root of 36 minus x squared from the x-axis to the top. And then from the x-axis to the bottom here, can you hopefully you can see it's the same length, right? But the y coordinate down here, that would be the opposite of the square root of 36 minus x squared. But that's a negative value. So we gotta like subtract it to make it positive, right? It's this length minus that length. So really what I have here is two of these, right? I've got this length and then the same length again. So this length of the slice here is actually 2 square roots of 36 minus x squared, right? So that's the length of the base of my square face here. Right? And if it's a square, then that should also be the height of this face. Right? 2 times the square root 36 minus x squared. So when I talk about, the area of the face, it's just, that value squared, right? You're multiplying length by width. So it'd be 4 times and then square root times square root, the square root's gone. It's just 4 times the quantity, 36 minus x squared, and then times dx, right? So here is the volume of one individual slice, right, at one particular x value. And then I'd be doing this slicing for every value from -6 to +6, and then adding those up, right? So we'll get an integral. So the total volume of the 3D figure being described here be the integral. And I'm doing this for every value from x equals -6 to +6 of our slice volumes, right? This 4 times 36 minus x squared times dx, right? Now, once again, you may see once again this nice symmetry here, right? The right half of the region here is exactly the same as the left half. So just like last problem, right? Just like the last example, this function for the area of our square, right? The area here, this is an even function again. Right? The value of this at -x would be the same thing as the value of this at x, right? So using symmetry once more, right, just like in the first example, this I can say then would be I'll just take, instead of going -6 to +6, I can find the volume from 0 to 6 and then just double that using some symmetry. So we'll double and then the area, the volume from 0 to 6, right? So I'm going 2 times the integral from 0 to 6 of our volume, our slice volumes. Okay, now this 4 can come outside, right? Constant multiples can be pulled out. So this is 8 times the integral from 0 to 6 of 36 minus x squared. And now I can, this is a nice simple sum here. I can just take the antiderivative very quickly. So it'd be 8 times 36x minus 1/3 cubed. And we're going from, 0 to 6. So again, the reason I did the symmetry thing is so that one of these values is just 0. Right. This doesn't always happen, right? I know it's happened for these first two examples. There's not always nice symmetry like this. So what I'm getting here is, plugging in 6, plug in 0, subtract them, but that'll just be subtracting 0. So really what I get here is just what I get when I plug in 6. So this would be 8 times, now 36 times 6 is 216. That's 180 plus 36, 216. Minus, and then 6 cubed is 216, right? It's 216 thirds. And if I factor, 216 out of this, 8 times 216, 8 times 200 is 1600. 8 times 16 is 80 and 48, so that's 128. So 1728, that's 12 cubed, 1728, 2 cubed, and 6 cubed, 12 cubed, 1728. Pulling 216 out, 8 times 216, 1728, and then 1 minus 1/3, right, when the 216s are gone. So that'd be 1728 times 2/3. The nice thing is, though, right, 3 goes into 1728 evenly. 3 goes into 1728. Let's see. So I'll divide by 3. 3 goes into 17, 5 times with 2 left over. 3 goes into 22, 7 times with 1 left over, and then 18, 6 times. So that's 576. I'll divide by 3. And then I still have the times 2, so the 1,152 for my integral here. And this is, again, cubic units. Cubic units. All right, so for these first two examples, I actually, when we integrate a polynomial, notice it ends up being some rational number. What I'm going to do from here on out is actually, for most of these anyway, not all of them. Some of them I'll show you if it's a function we haven't come across yet. But there's a nice graphing calculator online at a website called desmos.com, desmos.com, where you can enter your integrals very quickly. I just hit int, and I'm given a definite integral, and I can just put in the original one I had, -6 for the lower limit, +6 for the upper limit, and then 4 times the 36 minus x squared times dx for my integrand, right? And you see it's 1,152 cubic units, right? Which is what I got when I did it, by hand here, 1,152. So in the video in the future questions, when I realize that something's going to be rational, I'm going to go to Desmos and just type it in, right? Make things a little faster. And you can do that too, of course. All right, so back in the assignment, 1,152 cubic units. Wonderful. And again, they show you here where you can kind of see the three, it's a circle with all these square. All right, we can zoom out a bit. It's this 3D figure here, right, circular base, and then you got these square cross sections, right? They have a cross section in orange here, right? So you can play around with that stuff and find the volume of it, 1,150, and they go through the whole procedure. You check it out. Right. All right, next question. All right, so you see it was a little blip earlier on the progress circle. Now it's a bigger one, right? So again, the more you do correct in a row, um, the faster it'll complete. Don't get things wrong. Right. Forget when you get things incorrect in Newton Alta, they will throw more problems at you until they feel you have mastered it, right? Gotten several in a row correct. All right. So don't guess. So now we have another one in the same objective. I think they're having us because of the way the objectives are broken up. Right. Everything in a bold heading is done on its own before they move to another one. So I think we're going to complete this cross sections objective first before the others. So find the volume of the solid whose base is a triangle with these vertices. Slice is perpendicular. All right, so again, slice is perpendicular to the x-axis. Semicircles, right? Half of circles. And find the volume of the three-dimensional figure. All right, so back to my paper. All right, so the region that's going to be the base of this 3D figure is a triangle, they said, right? So we had a circle last example, a part of a parabola, like a parabola shaped thing in the first example. Here's a triangle. 0, 0 is one of the vertices. 0, 5 is another vertex. And then 5, 0, another vertex, right? So here's the region that's the base of this figure, this nice right triangle shape here. So there's the base, triangular base of this three-dimensional figure. And they told us, you can imagine something's popping out at you but when you look at it from above, you're seeing a triangle, right? They told us that again, we're slicing once again perpendicular to the x-axis, right? So I go to some value on the x-axis, between 0 and 5 here, make a slice, perpendicular. So once again, I'm going to think about this as some thin rectangle. So here's a slice. And we would be doing this, for every value from 0 to 5. So when I integrate later, the limits of integration are 0 to 5. All right, so if I pull this slice out, again, the thickness we'll call dx, right? It's delta x, but we'll call it so thin, going to 0, we'll call it dx. All right, so if I pull this slice out, it's going to look like this. So this time, it's again going to be super thin. The faces of these slices are semicircles. So half a circle with this thin little rectangle on the bottom. So, like this, really thin. It's not a great drawing, but with this thin rectangle on the bottom, something like this. But these are semicircles, right? Half circles. Again, the thickness will be, I'll call it dx. And then what I want now is the area of the semicircle. Now remember, the area of a circle, a full circle, is pi times the radius squared. Okay, so this will be half that, half pi times the radius. So let's say this is the center here. This will be the radius of the semicircle, which will be half of this length here, right? So this, so we're looking for, here would be the diameter. The diameter is the length of my slice. And I want this, right? I want this in terms of x, right? We have dx and stuff. So the diameter, right? That's just the y coordinate here. And this line here, very simple, would be, y equals negative x plus 5. Right? It has a slope of -1, right? The rise, down 5, right 5, run, so -5 over 5. It has a slope of -1 and a y-intercept of 5, right? So this diameter is, negative x plus 5. So whatever x value I'm at, it says negative x plus 5 or 5 minus x. So my radius, right, the radius is half of that, right? Half of 5 minus x, or half of negative x plus 5, okay? All right, so now the volume of a slice, volume of a single slice here would be, the area of this semicircle. Now the area of a semicircle, again, is half the area of a circle, half of pi r squared. So half of pi, and then times this radius in terms of x, half of 5 minus x squared, right? Half of pi r squared, and then times the thickness, right? Again, it's the area of the face, the area of the cross section, times the thickness, times dx. So there's the volume of a single slice at one particular x value. I'm going to simplify this a tad. Right here, when I square a half, that's a quarter, and then times this half out here, that'd be 1/8. So I'd have 1/8 pi, and then you have the 5 minus x also being squared. Oops. 5 minus x also squared, and then times dx. So I'm going to look at it this way. Okay, and then the total volume. So then the total volume of the whole 3D figure, right? I'm doing this slicing, taking a look at a slice for every value from 0 to 5 on the x-axis. So I'm going to do the integral from 0 to 5 of these slice volumes. We're adding up these slice volumes. So pi over 8, right? 1/8 pi over 8 times 5 minus x squared dx. Okay. Now I'm going to pull out the pi over 8, right? And then we're integrating from 0 to 5. That's 5 minus x squared dx. And I'm just doing this one on Desmos. Okay, because the integral of a polynomial is going to be if your limits of integration are rational and you're integrating expressions with rational powers and rational coefficients, you'll end up with a rational value, a polynomial. You'll end up with a rational value. So I'm just going to enter that integral back in the Desmos site. So that integral, after I pulled pi over 8 out. So whatever I get here, I'm going to multiply it by pi over 8. You have 0 to 5 of, and then the expression, the integrand was the quantity 5 minus x squared. All right, so that's 41 and 2/3 or 125 thirds, right? I just hit a little, there was a button off to the side here. You can't see it. It has you can change this to fractions. So it's 125 over 3. Then remember, I'm multiplying this by pi over 8. So the denominator is 3 times 8 or 24. All right, so the total volume is going to be 125 pi over 24 cubic units. All right, so back on the assignment, that's what I shall enter. 125, and then they got the pi symbol down here, divided by 24 cubic unit. Great. And again, I think they have a little picture of the figure. Here it is. See, if you look at it from above, right? If you look at it from above, you're seeing the triangle, right? That's what you're seeing, the triangle base. But if you look at it from the side, right, you're seeing your semicircles, semicircle cross sections. Yeah, there's your 3D figure. And we just found the volume of it. Wonderful. All right. Next question, probably from the same objective, right? Now we're halfway done. That's 3 questions in. So I'm guessing there's going to be 5 questions for this objective. All right. So once again, we're finding, volume, integrating finding cross sections, taking slices out, looking at those slices, and then adding them up through integration. All right. So find the volume of the solid whose base is in the first quadrant, bounded by y equals square root of 7 minus 7x, the x-axis, and the y-axis, right? X equals 0 is just the y-axis. Using equilateral triangle cross sections perpendicular to the x-axis, right? So equilateral triangles. Okay, so enter, using exact values. Back to the paper. So I'm going to draw this region that's going to be the base of our 3D figure. So the curve given to us here was y equals the square root of 7 minus 7x. So this will have, this has the point 1, 0. Got 0 square root of 7. Maybe I should make this big, actually, sorry. So here's 1, 0. It's got 0 square root of 7. And it's some, it's like part of half of a half parabola shape, part of the square root function going that way. And we're also bounded by, x equals 0 and the x-axis, right? So the base is this thing here, right? This region here. So there's the base of this 3D figure. And then something's popping out of it, right? It's a 3D shape. And if I looked at it from the right or from the left side, right? If I look at a slice perpendicular to the x-axis, we're going to see an equilateral triangle. Right, so I'll do my slices again. So now I'm doing slices from 0 to 1 on the x. I'm doing, perpendicular to the x-axis. So if I went to some x value here, I made a slice. Think about the slice as some thin rectangle. And let's look at that slice down here. Pull that slice out, and it would look like this. You'd have an equilateral triangle as the face. And again, it's just a thin slice here. I'm not the greatest artist, I'm sorry. But there's an equilateral triangle as the face, right? These equilateral triangle. And again, the thickness of this we'll call dx, right? That's the thickness of the slice here. Okay, now all I need now is the area of an equilateral triangle. Now remember the area of a triangle, let's look at equilateral triangles over here, is base times height. So you remember equilateral triangle, right? All three side lengths, let's say they're all b, they're all the length of the base. And you got 60-degree angle here, right? This is a 60-degree angle. And when I cut this in half, right, then you'd have half b, and there's 1b, and remember the height is the square root of 3 divided by 2 times the base. So the area of an equilateral triangle is half the base times the height. So we get, square root of 3 divided by 4 times the base squared. Right? This is the area of an equilateral triangle. Square root of 3 over 4 times the base squared. So that's what so all I need here is to find this base, and so see how the base, find the length of one side because it's the length of all three sides. The base of this triangle is just the length of my slice, which again is the y coordinate of that point from 0 to y. That'll give me the base of this triangle down here. And if I want, if I have dx, I want things in terms of x. So the y coordinate here in terms of x is given by the curve, right? The y values on this curve are the square root of 7 minus 7x. That's the length of this slice here. That's the base of this equilateral triangle. All right, so based on what I just said over here about equilateral triangles and their areas, the volume of this slice, right, V slice, is the area of our base. So the square root of 3 over 4 times the base squared, right? Now when I square the base, the square root will be gone and you'll be left with just 7 minus 7x. And then times the thickness, right? So there's the area of the face, the area of the cross section, times dx, times the thickness. And if you'd like, I can pull the 7 out, factor a 7 out of this linear here. It'll be 7 square root of 3 over 4, and then just times the integral of 1 minus x. Right? And we'll be doing this for every value of x, from 0 to 1. Now, I know I could go to Desmos for this, but because we're only going 0 to 1, and it's just a linear polynomial here, I'll do this by hand. It shouldn't take that long. So then the total volume of our 3D shape, right, is going to, I'll do this slicing for every x value from 0 to 1, right? So the integral from 0 to 1 of these slice volumes, right? So 7 times the square root of 3 over 4 times 1 minus x times dx. And I'll pull the 7 square root of 3 over 4 out, right? That's a constant multiple. And I'll just do the integration, right? When I integrate 1 minus x, that's, x minus half x squared. We're going from x equals 0 to x equals 1. I plug in 1, I plug in 0 and subtract them. Well, when I plug in 0, that's nothing. So it really is just what happens when I plug in 1. And when I plug in 1, that's 1 minus a half. So half. This times a half makes 8 in the denominator, right? So you have 7 square root of 3 over 8 cubic units for the volume of the shape they are describing, right? The solid they are describing. All right, so let me enter that. So 7 square root of 3, get out of the square root there, divided by 8 cubic units. drawing, and they probably have a picture of the shape here. Let me zoom this out a bit, right? So if you look at it from above, you should see. If you look at it from above, you can see that kind of square root function we were talking about, right? Or this isn't fully above. And then if you look at it from the right side, you'll see these equilateral triangles, right? So the equilateral triangles are what those cross sections look like. Every cross section that's perpendicular, every slice that's perpendicular to the x-axis. The volume of that was, 7 root 3 over 8 cubic units. All right, so look at that. We're barely anything left in this, right? So one more question here. All right, so this is find the volume of the solid ball base is a circle with a radius of 21 that has cross sections perpendicular to the x-axis that are equilateral triangles. It's back to the paper. So keep this in mind. Right? This happened last question. They said the cross sections were equilateral triangles. So we'll have slices looking like this again. Triangle face with some little thin thickness there. But remember, the area of an equilateral triangle is the square root of 3 over 4 times the base squared, right? Times the side length squared. So I'm going to keep that in mind. I'm going to bring that back up when I draw my next picture. So we have this circle with a radius of 21. I'm just going to put this at the origin. Right, here we go, right? Here's the region in question, right? This isn't a great circle, but so here's this, circle with a radius of 21. And remember the equation for a circle with this radius would be centered at the origin would be x squared plus y squared equals, 21 squared, which I think is 441, right? Yeah, 441. And then if I were to solve for y, right, the top half of the curve has this equation. The y coordinate is the positive square root of, 441 minus x squared. And the bottom half of the curve, the y coordinates are, the negative square root of 441 minus x squared. If I were to solve that circle equation for y, get the top half and bottom half. All right, so when I do a slice here, they're saying, so again, stuff's popping out of this. It's a 3D figure. And when I do a slice perpendicular to the x-axis again, right, so I'm going from, anywhere from negative 21 to 21. If I make a slice at some x value, think about it as some thin rectangle. Here's what the slice looks like when I pull it out. The face of the slice is an equilateral triangle. Again, right? So equilateral triangle, and then behind it, another equilateral triangle. And I'm not the greatest at drawing. And then there's a little thickness, right? And this, you have this little rectangle on the bottom. That's my slice, right? That's my picture here. This thin rectangle is on the bottom. And the thickness we'll call dx, right? The thickness is a little dx, and what I want is the base, right? That's the base of this in terms of x, right? Because my thickness is dx, I'm going to be integrating with respect to x. Well, this length here from the x-axis to this curve here, in terms of x, that's the square root of 441 minus x squared. And then this distance, can you see with the symmetry that it would also be the same? I mean, the y coordinate is the negative square root of 144 minus x squared, but I want to make that positive, right? Make it a positive length. So really I have two of these, right? It's 2 times the square root of 441. I wrote 144 there, sorry. 441 minus x squared. And recall that the area of equilateral triangle was the square root of 3 divided by 4 times the base squared. I saw that in the previous example, or some example, the example before this one. Okay, so the volume of a slice, right, just one slice here, is the area of my face, the area of the equilateral triangle, right, the area of the cross section. So that'd be square root of 3 divided by 4, and then times the base squared, right? So this 2 times the square root of 441 minus x squared, and then times the thickness, right? The area of the cross section times the thickness. Now, if I simplify this a tad, when I square the 2, that'll be 4, that'll cancel with this 4, so I have just the square root of 3 now out here. And then square root squared, gone, right? So I have just times the quantity, 441 minus x squared, times the thickness, dx. And I'll be integrating this from negative 21 to 21. And now you can use symmetry, right? Because again, this is another even function here. So instead of going negative 21 to 21, I can go from 0 to 21, find that volume, and then just double it. But this one I'll put in Desmos, though, because once again, I have a little polynomial here. I'm going to pull the square root of 3 out. So the total volume, I'm just going to pull the square root of 3 out right now, because that's a constant multiple. The square root of 3, times the integral from negative 21 to positive 21 on the x-axis. I'm doing this slicing for every value from negative 21 to 21. Of this, 441 minus x squared polynomial. And this should be something real nice. Again, ignore the square root of 3 for now. I'm going to integrate this in Desmos. Because it's the integral of a polynomial, and my limits and coefficients and whatnot and powers are all rational. The value should be a rational number, some fraction. So just changing my integral here from negative 21 to positive 21 of, and then it was 441 minus x squared, but just that, right? Not, it didn't have raised to the second power after that, right? So there. So 12,348. And then this is, of course, times the square root of 3. Right. So this is 12,348 times the square root of 3, cubic units. Sorry about the tightness. Cubic units, volume. So about the close to the edge there. Yeah, so that's what I'm typing in. So 12,000. Let's make sure I answered that correctly. Yeah. 12,348 times the square root of 3 cubic units. All right, great. And again, they have the picture. They probably have the, here's the shape down here, right? You see, if I look at it from above, right? If I look at it from above, you can see the circular region that we were starting off with, a radius of 21, center of the origin. And if I look at it from the right side, right, you see these equilateral triangle cross sections. And really, the cone, well, not really, actually. That's more like a little cone. When I looked at it this way, it looks conic, but like a little duck bill that's closed. Anyway, volume of it is the value we get, right? Cubic units. All right, so that's it for that objective. All right, where you're given the base on the XY plane, and then you've got cross sections that you're trying to find the areas of. So now we're moving on to they're called solids of revolution. So this time, from here on out for the rest of the video, we're taking a region on the plane We're going to take that region and rotate it around the x-axis or the y-axis or some vertical line or some horizontal line, and that'll create a three-dimensional figure, three-dimensional solid figure. And then we're asked to find the volume of that figure. And it's very similar to the slicing thing we were doing in the previous objective, right? So I'm going to take little slices of the region, little rectangles, thin rectangles, and see what happens to these thin rectangles when I rotate them around the x-axis or the y-axis or some other horizontal or vertical line. And after we see what happens to one thin slice when we rotate around some line, then we're going to add all the volumes up by, integration through integration. So it'll be pretty similar to that objective with the cross sections from earlier in the video. All right, so my first example is on the objective. Find the volume of a solid of revolution using the disk method. So if you recall what we were doing in the cross-section objective, I was making slices, perpendicular to something, right? Perpendicular to the x-axis. We didn't see any problems with perpendicular to the y-axis, but you may. So with this disk method, later in the video, we'll see something that's called the washer method. It's just the disk method again, but with a washer is simply a disk with a hole in it. So one big disk with a little disk taken out. But with this disk or washer method for finding volumes, we're going to make our slices perpendicular to the line that we are rotating around. Right. And I'll point that out with each example. All right, so here we're defining some region on the xy plane bounded by the graph of f of x equals x cubed over 6 plus 1, the x-axis, x equals 0, and x equals 1. All right, so it's really just this curve over the interval from 0 to 1. And we're using the disk method to find the volume of the solid of revolution when r is rotated around the x-axis and submit an exact answer. So first let me draw this region they're describing. So yeah, they said y equals, 1/6 x cubed over 6 plus 1. And we have the x-axis, x equals 0, x equals 1. So we're going just from x equals 0 to x equals 1 here. And it's going to be the area under this curve, the region under this curve to the x-axis over this interval. So you got the point 0, 1. All right, the point 0, 1. And then if I plug in 1, we're getting 1 and 1/6. All right, so 7/6. It's 1 and 1/6, right? And it's just, you know what cubics look like. They're like this here would just be the usual cubic, but squashed by a factor of 6. You have a vertical compression by a factor of 6, and then it's moved up 1 unit. So it's like woohoo, and then something like this, little curve there. Yeah, and then from x equals 0 to x equals 1. So we're talking, this region right here to the x-axis, right here. So there's R, the region R we're talking about. Now, if I were to rotate this region around the x-axis, I'm going to put a little loop here. So if I were to rotate this, I'll try my best to draw a picture of this. I'm sure they'll have like a graph of it when I, see the answer explanation in Newton Alta here. But let's try to draw a picture of it right now. If I rotate this region around the x-axis, we're going to get a 3D figure looking like this, right? You got this on top, and it'll be across the x-axis, and you'll have something like that on bottom again, right? Just the rotation of it, and a bunch of circular cross sections. Because if you do a rotation around something, that's revolving, it's creating a circle, right? So you'd have the x-axis going through the dead center here, and you got this, this 3D shape. This isn't great, but it's a three-dimensional figure like this. Okay, maybe we'll see it, when we see the answer explanations, as I said earlier. All right. So to create a disk, I'm going to talk about using the disk method. To create a disk, or later we'll see something called a washer, which I said earlier, right? A washer is simply a disk with a disk cut out of it, right? It's a disk with a hole in it. Slice perpendicular to the line you're rotating around. I'll say the line of rotation, or you could say axis of rotation. All right, so in my picture up here, if I'm doing perpendicular cuts, that's going to correspond to some x value from 0 to 1 here, right? So I go to some x value, right, from 0 to 1, and I make a little slice. And just like earlier, right, with all those cross-section problems, think of this as some thin little rectangle. And the thickness of this rectangle will be some little change in x, right, some dx. Now, if I rotate the slice around the x-axis, we create, again, what they're calling a disk. It's just going to be some thin, little disk here with a circular. Disks and washers basically have circular faces. You get something like this, little circular thing with a little thickness, but you got circular faces. And again, running through the center of it would be the x-axis. I'll point out again, you have circular face, circular section. And so just like in the cross-section perspective, I want to find the volume of this little disk. And then once I have the volume of this little disk, I can do that for every x value, from 0 to 1 and add them up, right? Integrate. All right, now because the face is circular, right, it's going to have a radius. So let's say that's this distance here. Radius, I'll call it capital, the region capital R. I'll just call it R, right? R equals radius of circle, right? Radius of disk. And the volume of a disk, right? The volume disk, I'll put volume disk, right? The volume of a single disk is, just like your cross sections earlier. It's just the area of the face. So pi times the radius squared. There's the area of the face. And then times your thickness, right? And the thickness is dx, right? The thickness is this little change in x here. And now all I need to do is I want to get the radius in terms of x. Well, you see how the radius is just the distance from the x-axis to the point on top of this of the rectangle here, right? This would be the radius, right? From the x-axis, from the line of rotation through the curve that's being rotated, to the top of the region that's being rotated. And that radius would actually be, the y coordinate of the point on the curve. But the y coordinate of the point on the curve is, 1/6 x cubed plus 1, right? We're told that. So the radius is, 1/6 x cubed plus 1. And so the volume of a disk, just one little disk here for this problem, is pi times the quantity, 1/6 x cubed plus 1. So there's your radius of the disk squared. There's the area of your circular face, and then times the thickness dx. And we'll be doing this for every value of x, from 0 to 1, adding those up. So the total volume of this 3D figure that's created by rotating the region around the x-axis is the integral from 0 to 1 of this thing here. Right? So, because there's this pi here already, constant multiple pi, pull that out. All right, so pi times the integral from 0 to 1 of, the radius squared, right? 1/6 x cubed or x cubed over 6 plus 1 squared, dx. And we can now we'd have to multiply this out, polynomial, and then integrate. Again, because this is going to be a nice polynomial with all rational limits, rational coefficients, rational powers, I'm going to do this on Desmos just to save me some time. Okay, but if I were testing you, I would expect you to, expand that and integrate term by term, plug in 1, plug in 0, subtract, and then whatever your result is gets multiplied by pi. All right, so I'm going to enter this integral on the Desmos site. I had this from a previous problem. That integral is the integral from 0 to 1 of, and then the expression in the parentheses here should be x cubed divided by 6 plus 1. This is being raised to the second power, right? That's the radius squared. And then as a fraction, they're giving it to me here. If you don't have a fraction, there's a little button off to the side, off to the left side, that'll change it to a fraction if it's rational. 137 over 126 times pi. Don't forget the times pi. We put it out early. So this is 137 over 126 pi. And that would be in, right, cubic units, right? That was the volume. So I shall enter that back in the homework. I got the pi symbol down here, right? So 136. I'll just put the pi in the numerator. Sorry, 137. I don't want to get things wrong here because it'll throw more problems at me. Divided by 126. And hopefully they have a nice picture of it again. No, they don't. Oh, they do. Okay, here we go. So this is what's happening. All right, so this is that region I was talking about. All right, this is the region I had drawn on my page. And then what they do down here in the answer explanation is, all right, you can look at this and see what happens when I perform the revolution, right? The rotation. We're going to rotate this around the x-axis. And you see, oh, maybe I'll be nicer when I'm looking at it from that side, right? Look at what happens. I take this region and rotate it around the x-axis, right? It sweeps out this 3D shape. And you see the 3D shape. It's like the shape I had for you. I mean, I tried to draw a picture of it. It wasn't great, but it's a three-dimensional figure. With, when I look at it from the right, see the circular cross section. There's your discs. Red slice there is one of the thin discs of the whole thing, and then they just add up all the discs from, when x equals 0 to x equals 1. Okay, great. So another one with the same objective. Volume of the solid of revolution using the disk method. Okay, R is this region bounded by the graph of f equals, -4 times the square root of 3 cosine x. The x-axis, x equals -pi/3, and x equals pi/4. So I'll draw this region again, and then we're going to rotate this around the x-axis once more. We'll see some other ones, I'm sure, where we'll rotate around the y-axis. So we're going from -pi/3 on the x, they said, right? X equals -pi/3 to x equals pi/4. Say that's over here. And the x-axis is part of this too, right? So nothing below the x-axis. And the curve was y equals, or f of x equals, -4 times the square root of 3 cosine x. Right. Now, when you plug in, -pi/3, this is the square root of 3/2 times -4. It should be some negative number. Let me actually just go to, I'm just going to go to the calculator. So -4 times the square root of the cosine of -pi/3. It's about -2.8. All right, so I know that on the left here, it's down here at about -2.8-ish, right? It's approximately this point. Now, cosine of 0 is 1. I'm just going to plot some other points here. If I plugged in 0, I'm just showing you, but oops, sorry, I forgot the 3 in front of that. My apologies. So that should actually be about -4.9. Okay, sorry, I forgot this coefficient of 3. So that should be about -4.9 at -pi/3. Then at pi/4, about -5.8. I plug in pi/4, right, 3 root 2 over 2. So it's times -4, and then the square root of 3 root 2 over 2, and then times -4, about -5.8. So this point down here, and 0, it's -6.9. Right. When I go to 0, it's at -6.93 something, about 6.9. All right, and I feel like it's just going to be doing this, something like this. It should be kind of wavy, right? Because the cosine's wavy. Let's actually double check that. I just want to actually absolutely verify this. Well, let me just plug in there. So yeah, so it's kind of when I go from, well, there's pi/2 here, -pi/2. So from -pi/3, let me call this f, and then I can just do dot points here, right? -pi/3, comma, and then f of -pi/3. All right, so there's the point I'm starting at, right? This was at the -4.9-ish y value. And then the point on the right end of the curve, right, should be at pi/4, right? Pi/4, comma, and then f of pi/4. All right, so that's this, again, this should be at -5.8-ish, right? So yeah, this piece of the curve there. So my drawing's not too terrible. So it's just this piece of the little the bump there. And yeah, the region being talked about, right, is the region to the x-axis, they said, right? So this region here. And this region, they're telling us, is being rotated around the x-axis once again. Right? Now, I'm not going to draw it this time, but if I rotated this around, maybe I'll draw a small version of it. I'd get, this kind of curve down here, and then this, like the opposite of that up here. And then you have again all these circular cross sections. So you get some little, maybe like some little bowl-shaped thing here with the x-axis running through the middle, but you get some three-dimensional little bowl-looking thing, a little ball. And we're trying to find the volume of this. Um, it up, whatever. Yeah, not a great drawing. If I rotate this around the x-axis, I get a three-dimensional shape. What's the volume? Now, if they want us to create a disk, right? They want us to use this method. You make cuts, you make slices perpendicular to the x-axis. So I'm going to take, some x value here, from negative pi over 3 to pi over 4. Let's say x, right? Some x value, I make a slice. Remember, my slices, I'm going to think of these slices as little thin rectangles, and the thickness of this will be, dx. And, the length of it will be the opposite of this y coordinate. Right, because if I go from 0 down here, that's a negative y coordinate. So the length of this is the opposite of the y coordinate, and that's going to be the radius of the disk, right? When I take this thin slice here, when I take this thin rectangle and rotate it around the x-axis, sweep it around the x-axis, we create a disk. Some little thin disk, right, like a coin. And through the middle is the x-axis. We're rotating around the x-axis. And from this picture here, the radius, I can find the radius going from the x-axis down to the curve at the edge of the region. So radius. Now, can you see how, again, the radius has got to be the opposite of this y coordinate, right? Going down here to this y coordinate, the y coordinate is negative for this point. So I'm saying the radius is, it's got to be the opposite of the y coordinate, right? Which, if I have dx for my thickness, right, I want this in terms of x. So the opposite of y is, positive 4 times the square root of 3 cosine x. Okay. All right. And then the volume of a disk. All right, so the volume of just one of these little disks is the area of the circular cross section, right? The area of the circular face. So pi times our radius here, which is 4 square root of 3 cosine x squared, right? We're going to square that radius. And then times the thickness, right? Times dx. That's the volume of one disk. And I will be doing this for every x value, from negative pi over 3 to positive pi over 4. So the total volume of the 3D shape being created when rotating this region around the x-axis will be an integral. Total volume will be the integral from, x equals negative pi over 3, x equals pi over 4 of the, volumes of our disks here. Once again, I'm going to pull the pi out. I'm also going to pull 16 out and a 3. So 48 pi. Right, because this is pi. And when I square this, it'll be 4, it'll be 16. When I square this, I'll have a factor of 3. Right? The square root will be gone. And 16 times 3 is 48. 48 pi. I'm pulling out 48 pi, and then all I'll be left with is the cosine of x. Right? Because when I square this square root again, the square root's gone. It'll be the cosine of x. And then you got times the thickness, right? So there's going to be the total volume of our figure. And, this integral is pretty easy. So we got 48 pi And the antiderivative of cosine is simply sine. We're evaluating this, from x equals negative pi over 3 to x equals pi over 4. All right, so this is 48 pi times, now the sine of pi over 4, all right, that was half the square root of 2, right, square root of 2 divided by 2, minus, and then the sine of, the sine of negative pi over 3, because sine is odd, would be the opposite of the sine of pi over 3, so this would be plus now, and then the sine of pi over 3 was square root of 3 over 2. And if I pull a half out of this, right, both these have a half in common, I'll have 24 pi times the quantity, square root of 2 plus the square root of 3, and then that's, cubic units, right, for the volume of this 3D ball thing that I tried drawing when we rotate the region around the x-axis, and this is what I'll type in. So back in the homework. So 24 pi, oops, I forgot you can't type pi here. They have the symbol provided, times, and then the square root 2, that square root plus square root of 3, close parentheses there. All right, that should be good. Great. All right, and once again, they're showing you all the stuff. Now, I think they have you, there's the region, right? There's the region I drew. And they want you to check it out. Hey, look what happens when you rotate it around the x-axis, right? You sweep out this shape, this 3D shape, and they also have a disk there for you. Yeah, there's this 3D shape. Ooh, right, and then the disk, and you see the circles, the disks, and all that. And then the volume of that shape we found. Right? Nice. Next, same objective. So here, finding another region on the xy plane. We're going to rotate this region once again around the x-axis. That's y equals negative 2 e to the negative x, the x-axis, and then between x equals 0 and x equals 1. All right. So I'm going to draw this again as best I can. Maybe I'll go to Desmos and look at a better version of the picture. Never hurts. So this time we're just going x equals 0 to x equals 1 to the x-axis under this curve. So y equals negative 2 e to the negative x. Now that 0, right, e to the 0 would be 1 times negative 2. So it would be negative 2 for the output there. And then e to the negative 1 right at the other end. E to the negative 1 would be 1 over e. 2 over e is about 2/3. It's actually a little bigger than 2/3. So this would be negative 2/3 about. So up here somewhere. Definitely not beyond negative 2. So negative 2 over e, 2 times e to the negative first for the output on the other end. And it's an exponential. E to the negative x is like this, but then it's multiplied by negative 2. So we got, flip that over as something like this, right? Something like that. There's our curve. And we're going again to the x-axis over this interval from 0 to 1, right? So here's the region being talked about. Once again, we are asked to rotate around the x-axis. So that'll create a shape like this. We have this on the bottom, rotate it around, this on top, and all these circular cross sections, right? You'll get some sort of shape like this, almost like a funnel. Really open, without a hole in it though, right? This is a solid figure touching the x-axis. There's no gaps in it. So I get this solid, almost like a seat if you, turn it that way, a little seat, or a hat. I don't know. Okay, but yeah, some 3D figure. And again, we're asked to find the volume of this figure using the disk method. So I'm going to make cuts perpendicular to the line we rotate around. So perpendicular to the x-axis. So I'd be going at, if I want to make a little slice, a little cut, go to some x value here between 0 and 1, make a slice, which once again, I'm thinking of this slice as a thin rectangle. And the thickness would be some little tiny change in x. I'll call it dx. And again, this would be the y coordinate here, right? From 0 to y. So the radius of my disk, right? When I think of the disk that's being created here. All right, again, a little coin where the center of it is the x-axis, the line of rotation. To get the radius, right, I'm going from the x-axis to the bottom of this coin. Just like last example, right? See how the radius here, it's not just the y coordinate, but it'd be the opposite of the y coordinate. Because, that's a negative y coordinate. We don't want negative radii. So I'm doing the opposite of the y coordinate. And I want this in terms of x, right? This is dx, so I'm going to be integrating with respect to x. So in terms of x, the opposite of the y coordinate on this curve would be positive 2 e to the negative x. And then the volume of a single disk is going to be the area of our cross section, the area of our circular face here, pi times this radius squared, so 2e to the negative x squared, and then times the thickness. And if I were to simplify this, this would be 4 pi, right, because 2 squared is 2, times e to the negative 2x, right, e to the negative x to the second, multiply the powers, times the thickness dx. All right, so we're integrating this. We're doing this for every x value from 0 to 1. All right, so let's do this up here now. I got some space. So the total volume, all right, the total volume of my 3D figure here be the integral from 0 to 1, right, x equals 0 to 1, of these disk volumes, where, 4 pi is a constant multiple. I'm just going to pull 4 pi out. Then we have e to the negative 2x dx. And you can do a u substitution here if you want, but because it's a linear polynomial in the power there, it'll be easy to integrate. This will be 4 pi times antiderivative e to the negative 2x would be e to the negative 2x again, but then to counteract that negative 2, I'm dividing by negative 2, so negative 1/2 of that, right, times negative 1/2. If you were to differentiate this, you'd get this back, right? And then we're evaluating from x equals 0 to x equals 1. So I'm getting 4 pi times, when I plug in 1, it's going to be negative half times e to the negative second. So that's 1 over e squared. So it's negative 1 over 2 e squared. Because e to the negative second would put e squared in the denominator. And then when I plug in 0, e to the 0 is 1. So I get minus negative half times 1. So minus negative half would be plus a half. And if I pull a half out of both of these, that makes this 2 pi, right? So we have 2 pi times, and then 1 minus 1 over e squared. I'm going to put the positive one first, and then minus 1 over e squared. Or you could put e to the negative second, but there you go. This 3D shape here has this volume, right? This is this cubic units. Right, so I'm going to enter that. So 2 pi times the quantity. Oops. 1 minus 1 over e squared, like that. And that should be good. Beautiful. Yeah, they wrote it out with e to the negative second. They pulled a negative out, but it's the same value, right? So like I said earlier, several examples ago, if you enter a number that's equivalent to what they have, they just give it to you. And again, here's the region that was in my picture. Have you, check it out, rotate it around the x-axis. Look at this, like, again, that little bowl shape. And there's not hollow though. And the little red thing there is a disk. You can see the moving around all over the place, moving back and forth. Check out the 3D shape that's created, and we got the volume of it, right? The amount of space it takes up inside. Right. So another one where we're finding the volume using this dis method. This time, we have a region that we're going to be rotating around the y-axis, right? So if I'm doing disks or washers, I'm going to take a slice, perpendicular to the y-axis now, right? Always slice perpendicular to the axis of revolution. All right, so we have g of y equals -1 over the cube root of y to the y-axis, and then from y equals -3 to y equals -2, and rotating this around the y-axis. So once again, let's draw up the region. So we're going y equals, so there's x-axis, y-axis, y equals -2 to -3. So let's say here's -2, and then -3 would be below that, right, on the y-axis. So they have x equals, g of y equals -1 over, the cube root of y, which you can also think of as negative, y to the -1/3 power. That might help when we integrate later. Okay, now plugging in -2 for y here. Now this will be a positive x value, and +1 over the cube root of 2. This will be a little less than a half. Let's say there's 1 over the cube root of 2 here. So I got this point. And then I want to plug in 3. You pull out, y equals -3. Pull out the cube root of -3 is negative cube root of 3. It'd be +1 over the cube root of 3. And the cube root of 3 would be bigger than the cube root of 2, so 1 over the cube root of 3 would be smaller than, so I probably should have made this out here more. So 1 over the cube root of 3, it's jumbled. 1 over the cube root of 3 would be smaller, so you have a smaller x value, and then these will be connected somehow with some curve, and we're going to the y-axis, right? So this region here, this region here is being rotated around the y-axis, right? So I'll make a little loop for myself, and that would create a shape like this, right? You'd have that on that side, rotate around, you have the opposing shape here, and then all these circular, like a circular, right? All these circular cross sections where the y-axis is running through the middle here. But this is the shape created, right? 3D solid. And we want to find the volume of this 3D solid. Again, the dis method, washer method. You're doing slices perpendicular to the line you're rotating around. Right, so I rotated around the y-axis. So I'm gonna now a perpendicular that will be a horizontal slice, and every horizontal line corresponds to some y value, right? So I'm gonna pick a y value here between -2 and 3, make one of these slices, and I'm thinking of each of these slices as some thin rectangle, and this time the thickness will be dy, right? Some little change in y. If I rotate that little slice, that little rectangle around the y-axis, I'll create this disk, just looking like this. Again, it's just like a coin with thickness dy, and the center of the disk is what we rotated around. The center should be at the y-axis here. And then from the picture, how I would find the radius of this disk would be to go from the y-axis through the curve on the right edge. So now can you see how the radius here must be the x coordinate of this point here? but I want to get things in terms of y. I have dy, and the x coordinate of this point on this curve has, this as the x coordinate in terms of y. It's negative y to the negative 1/3 power. So now I have the radius in terms of y, I got the thickness. We can say the volume of this disk, right? The volume of a disk is, the area of the circular face, the circular cross section, times the thickness. So pi times our radius, right? This negative y to the negative 1/3 squared, right? Radius squared, then times the thickness, which is dy. And if I simplify this a bit, when we square this, it'll be positive y to the negative 2/3, right? So it's pi times y to the negative 2/3 times dy. And then the total volume, right? This is the volume of one little disk. Be doing this for every single y value from -2 to 3. So I'm going to integrate, well, I should go bottom up, right? Go low to high here. So from -3 to 2, to -2. So yeah, but I'll be doing this. If I did from -2 to 3, I'll just get a negative number. You would just take the opposite of that, right? Just make it positive if you make that mistake. But the total volume then of the 3D shape, the 3D solid, would be the integral from y equals -3 to y equals -2 of these disk volumes. And again, pi is a constant multiple. I'm just going to pull that out right now. Pi times, then you have here y to the -2/3 power dy. Okay, this is easy to integrate. Pi times, and then antiderivative of this would be y to the 1/3. Right, so the cube root of y times 3 times the reciprocal of the new power. And we're evaluating from y equals -3 to y equals -2. Right, so pi times, now when I plug in -2, the cube root, this is the cube root of -2, which will be negative cube root of 2. So this will be -3. I'll write the cube root thing, cube root of 2, 2 to the 1/3. And then minus, and then when I plug in -3, it'll be the cube root of -3 here. So negative cube root of 3. So it makes this plus 3 cube root of 3. And I can factor a 3 out. This will be 3 pi times, and I'll put the positive one first, the negative one second. Quantity, the cube root of 3 minus the cube root of 2. Cubic units, right? This would be the volume of our shape. Right? And I'll just enter this. Right? So going back to the homework. Right, so we have a 3 pi times the quantity. I could put just 3 to the 1/3 power, but they got a nice little cube root thing here. I can go, I can put cube roots, right? Cube root of 3, and then get out of that. Minus, oops, I'm not going too far out. Minus, and then the cube root of, and that should be good. Right. And they kept the negatives in there, whatever. All right, and then again, they're showing you the region, right? This was our region. And then what happens when we rotate it, around the y-axis, right? So let's see this region when we rotate it around the y-axis, right? You see it creates this 3D figure. Right? There's a slice of it on the disk with the red. And, we found the volume of this 3D shape that was created. Right. Great. So it looks like based on the progress we've been making, probably just one more due in this objective. So another one where we're rotating around the x-axis. But this time, Look at this time, right? This time they're only asking us to set up the integral. Set up the integral, that's it. All right, so I'll still write it out. So the curves, right, the curves were given here. Y equals x cubed over 6, right? So first I'll do this. Draw our region. So y equals x cubed over 6. And x equals 0, x equals 2 in the y-axis. So x equals 0, x equals 2, sorry, in the x-axis, at the x-axis. Now 0, 0 would be on this graph, 2, and then 8, 2 cubed is 8, 8 6, this 4/3. 4/3 up here somewhere is on the graph, and it's just part of a cubic. It's this thing here, and we're just over this interval to the x-axis, right? So there's the region that we're rotating. And we're rotating around the x-axis. Right, so we'd create a shape like this. It's almost like a tornado shape. Right? You have that on top, that on bottom, and then a bunch of circles. Right? Kind of like a tornado shape. And what's the volume of that tornado? So if I'm doing, again, if I'm doing disk method, washer method, you're making a slice perpendicular to the line that you're rotating around. So a vertical slice corresponds to some x value as a thickness of dx. And remember the disk that's created from this then would look like this, right? Some vertical thin coin, vertical thin disk. Where in the middle here is the x-axis. And to get the radius of this circular face, right, that would be this length here, right? Now the radius is actually, the y coordinate, right, from y equals 0 to y equals whatever, of this point here on the end of the slice, on the end of the rectangle. But I want that y in terms of x, which is, x cubed over 6, right? I'm on the curve y equals x cubed over 6. So the volume of just a single disk is, the circular face area, I times x cubed over 6 squared, right, times the thickness, dx. And then the total volume, and this is the integral that we're going to have to set up. Right? The total volume would then be, I'd be making these slices and creating these disks for every value of x from 0 to 2. So I'm integrating from 0 to 2 of this here, pi. Now we could go pi over 36, right? Because 6 squared is 36 in the denominator, and then x cubed squared is x to the 6th dx. And this is all they want. Right? This is all they want. Enter the integrand and the limits of integration. So you see here the lower limit is from 0, upper limit to 2, and then in here, where I said it was pi over 36 times x to the 6th power. Right. That should be good enough. Right. Wonderful. And again, they probably had the same thing where here's the region we were shown, here's the region I drew, and if I rotated that around the x-axis, right, you can see the creation of this tornado shape. Right, a little tornado looking thing here. And we just found, and the red circle there is a slice of it, right, a disk, and we found the volume. Well, we found an integral for the volume. You'd actually have to go through and actually do the integration to find the actual volume. Right, so that objective's done. Now we're still doing, disk washer method here. We're still doing these volumes of revolution. So the procedure is not changing. But this time, right, for this objective, find the volume of a solid of revolution with a cavity, right, with a cavity, some hole in it, using the washer method. So remember I said earlier, washers are just big disks with little disks cut out of them in the middle. So let's see what happens here. All right, so once again, we're asked to just set up the integral that would provide the volume of the solid created. So here I'll got some region on the xy plane. Find region R as the region bounded above. So this parabola is on top. This line is on the bottom, and we're going from the interval from x equals 2 to x equals 4. This time, instead of rotating around the x-axis or the y-axis, I'm rotating around some other line. And it's another horizontal line, right? They say the solid created by rotating r around the line y equals -2. Right? So that's going to change how I determine radii, radiuses. It's not going to be to the y-axis. It's going to be to the line y equals, or sorry, not to the x-axis, but to the line y equals -2, another horizontal line. All right, so let me draw this. Draw this region being described, and I'll try my best to draw the 3D shape that would be created. All right, so again, we're only going from x equals 2 to x equals 4. One of the curves was y equals x squared divided by 3. The other curve was y equals just half x divided by 2. Right. So x squared over 3, when I plug in 2, that'd be 4/3, 1 1/3. So there's that point on first graph, and plug in 4, that's 16/3 or 5 1/3, something up here, 16/3, a little higher. Right, and this is part of a parabola. All right, that's kind of shooting up, right? The parabola this isn't a great drawing, but it's part of a parabola. It would be actually swooping. It would be a little steeper than that, actually. But there's x squared over 3, that y equals there, right? Then the other one's just a line. All right, y equals half x is just a line. Half of 2 is 1, which is under 4/3. And then half of 4 is 2, which is a bit above 4/3, right? That'd be 6/3, but over here. It's definitely under 16/3. Right? And it's just a straight line. Uh, This here, there's half x, y equals half x. And so the region being discussed here is this region. All right, that's region R being described. Now, right now, instead of rotating around the x-axis, right, that horizontal line, we're rotating around y equals -2, right? So here's y equals -2. And we're rotating around this. Okay, so the 3D shape created here would look something like this. You'd have this on top. And I'll just do the line dash because it's like going to be inside, and then same thing over here, and then this on bottom, and you know these circular things here, and a circle here. And not the greatest artist. Right. It's going to be some three-dimensional shape with a hole in it, with a cavity, they're calling it, right? But the line going through the center is y equals -2 now, right? Not the x-axis. Right? So what we do now is like we did with the disk method, right? They said use washers, these things called washers. If I'm doing disk or washer, right, I'm going to make a slice perpendicular to y equals -2, perpendicular to the line we're rotating around. So that'll be a vertical slice, and if every vertical slice corresponds to some x coordinate, right? So I take an x coordinate here between 2 and 4, and I make a slice in this region over that x coordinate. Right, so here's a slice, right? Or just a little thin rectangle, and it's going to have thickness, dx. And then when I rotate this, when I rotate just this slice around the line, we create what's called a washer. Because again, just it's basically right. It's a big disc with a little disc cut out of it, with a hole in the middle. And here, the line, y equals -2. Now the volume of a washer. Okay. Again, I told you already, it's a big disc with a little disc cut out. So see, these are still circles. All right, the faces of these are still circles. So when I want the volume of the washer, if I take the area of the face times the thickness, again, the thickness is dx. The area of this face is the area of the big circle minus the area of the little circle that was cut out. So I need a big radius, right? So I'm going to call this outer radius, RO, for outer radius. And then the radius of the little circle, I'm going to call it RI, or R1, for inner radius, RO, RI. Right? Outer radius for the big circle, inner radius for the little circle. And the volume of a washer. So again, it's the area of the face, which is the area of the big circle, so pi times RO squared, minus the area of the little circle, pi times R1 squared. Notice both of those have pi in common, so I'm going to factor that out. So you have pi times the quantity, outer radius squared minus inner radius squared. There's the area of the face, the area of the cross section, right? And then times the thickness, right? Times, here it's dx. And sometimes it might be dy. And now what I'd like to do is find this outer radius and this inner radius, right, so that they're in terms of x. Well, you see from here, the inner radius is the distance from y equals -2 to the bottom of the region. So on my picture here, this would be the inner radius, right, R1, Ri, from the y equals 2 to the bottom of the region. And then this outer radius, right, the radius of the big circle, is the distance from y equals -2 to the top of the region. So the top to the top of this rectangle. So there's RO. And I'd like both of those in terms of x. Hopefully you can see that, this point on the top of the rectangle has some y coordinate. I'll call that YO. That's going to help me find the RO. It's going to help me find the outer radius. And then the point on the curve on the bottom of this rectangle also has some y coordinate. I'll call it YI or Y1. All right, because again, that's going to help me find the inner radius. So you see how the RO, this outer radius, it's that y coordinate to the top curve, so YO, that's just to the x-axis, right, the y coordinate, and then +2, right, because I'm going down 2 to get to this line. So again, it's just top minus bottom, really. Top y, YO, minus bottom y is -2 here. Y minus -2 is y, so YO +2. And what is YO, right? The y coordinate on the top curve is this 1/3 x cubed. Right? So, x squared. X squared over 3 plus 2. So there's the top radius, the big radius, the radius of the big circle. And then RI or R1, and this here you got the y coordinate for the bottom curve, which is just from the x-axis, right? So there's y1 and then +2 again, right? You got to add 2 more units to get down to the line you're rotating around. So Ri is yi or y1 plus 2, or again, top minus bottom, y1 minus -2, y1 plus 2, which, and I want these in terms of x, y1 is the y coordinate on the bottom curve, which is, half of x. Given to us as half of x, or x over 2. All right, so putting those into my washer volume, all right, the volume of a washer in this particular instance is pi times and the outer radius squared. So this quantity x squared over 3 plus 2 squared. All right, that's the outer radius squared minus, all right, we're taking away that hole in the middle, the circle in the middle, the inner radius squared, which was, half x plus 2, right? X over 2 plus 2 squared. And then times the thickness, right? So there's the area of the face, right? The area of that ring, the big circle with the little circle cut out, times the thickness. And we'd be doing this, right? Creating these washers for every value of x from 2 to 4, and then adding them up, right? So the total volume here, right? So the total volume would be the integral from 2 to 4, right? X equals 2 to x equals 4 of this thing, right? Of the volumes of our washers, pi times the quantity, the quantity x squared over 3 plus 2 squared minus the quantity, x over 2 plus 2. That's that inner radius squared, and then close the big one, and then times the thickness, right, dx. And this, right, this is all they're asking for. I know it's a lot, but it's all they're asking for. They don't want an actual number, right? We could go through and multiply this out or put it in Desmos or whatever and get a number for the volume. But what they want is us to enter these limits of integration in the integrand. So back on the assignment here, right? The lower limit we said was 2, and the upper limit is 4. And then in here, the integrand, right? We had pi times the quantity, other quantity with x squared divided by 3 plus 2, that quantity squared, and then minus, right, drop down, go minus, and then another quantity, the inner radius squared, x over 2 plus 2 squared, and then close the big set of parentheses, and that's it, right? This integral is going to give us our volume. Great. Now they actually multiplied those out and combined like terms and whatnot, but as long as you're entering something that's equivalent to what they got, it should be given the problem. And again, they show you the region here, right? Region that they described. And here, rotate that region around the line y equals -2, and you're seeing this, thing with a hole in it. Right? It's like a hat with a hole in it, like almost like a really totally round visor. Got a red slice there. See that little thin red slice? That's your washer. That's what a washer is. A thin. You see, it's just just a disc with another disc cut out of it. And yes, and then we have the volume. Well, we have the integral to give us the volume of that shape, and of course you could just integrate and then find the volume of that 3D shape. Great. Let's go on. So, yeah, so still in this objective. Okay, so in this question, they had the region defined for us again. This time it's a multiple choice. So just what integral would give us the volume of the solid when we rotate this region around the x-axis. All right, so I will draw it. Maybe you see it already. Maybe you've seen enough examples now to where you can figure out what curve is on top, what curve's on bottom, and that kind of stuff, how to find the outer radius and inner radius. But I'll draw the region being described. So one function was y equals x cubed over 6. The other one is just y equals 1, g of x equals 1. And we're between x equals 2 and x equals 3. That's it. All right, so x equals 2, x equals 3. Now y equals 1 is, a horizontal line. We have 2, 1, 3, 1, right? Every point in here has a y value of 1. F of x, y equals x cubed plus 6 has 2. When I plug in 2, you'd have 8, 6. Again, that's 4/3. And when I plug in 3, that's 27 over 6. Or 9 halves, 4.5. That's part of some cubic function, right? This isn't a great drawing, but it's scrolling up, increasing. And over the interval from 2 to 3, right? So this region here is the region being discussed. And again, we're rotating around the x-axis, all right? So if I'm doing discs or washers, like here there's clearly a gap to the x-axis, so there's going to be holes in my discs, right? So these will be washers. I make a slice perpendicular. Take a piece of this that's perpendicular to the x-axis, perpendicular to the line we're rotating across. And if I'm taking a vertical slice like this, that'll correspond to some x value. It's got a thickness I'll call dx. And we'll create this washer. When rotating this little rectangle around the x-axis, I'll create this washer. And just like a coin disc with a disc cut out of the middle here, right? Like a hole in the middle. And the line going through the center of that hole, the x-axis, right, the line we're rotating around. I need the inner radius, I need the outer radius, right, to be able to tell you the volume of this washer. And I would like these, since the thickness I'm calling, dx, I would like these to be in terms of x. Now on the picture here, the outer radius is just the distance from the x-axis to that top curve, which will just be the y-coordinate of that top curve, right, from the x-axis to that y-coordinate. And the y-coordinates on that top curve are x cubed, the x-coordinate cubed over 6. And the inner radius is just 1. The inner radius is the distance from the x-axis to the bottom curve, and that's 1 unit the entire time. All right, so the volume of just a single washer here, remember it's pi times the quantity, right? It's the area of the large circle minus the area of the small circle that's cut out, and then times the thickness. So pi times, the outer radius squared, so x cubed over 6 squared, minus, the inner radius squared, just 1 squared, and there's the area of our of our little circular face with a circle cut out of it, right? That ring. And then times the thickness times the x. And we'd be doing this, finding these washers for every value of x from 2 to 3. Right, so the total volume of the shape created by rotating this region around the x-axis would be the integral from x equals 2 to x equals 3 of, our volume of the washers here. I'm just going to put that here, and that's what we're going to choose. Right? Pi times and then x cubed over 6 squared minus 1 squared times dx. And that looks like this second choice here. From 2 to 3 of pi times, x cubed over 6 squared. That was the outer radius squared minus 1 squared, the inner radius squared, and then times the thickness. Great. All right, and then down here they do the same thing where here's a picture of the region. And then that region, let's see what happens when we revolve it around. You start creating this three-dimensional shape with a hole in it. All right, there's this hole there. Right, you can see the hole in the graph. But it's this three-dimensional little disc. It's kind of like a visor again. And there you go. And we found and we set up the integral to help find the volume of the shape. So now we're on a different objective, but it's still washer method. But this time, instead of revolving around some horizontal line, we're going to revolve around some vertical line. And then our slices, our little thin rectangles, when we make cuts or slices, will be horizontal. One that slices perpendicular to the line of rotation. All right, so once again, we're just asked to set up the integral. All right, so I'll draw this region once again and rotating it around the y-axis. You'll see what kind of washer would be created, find the volume of one washer, and then integrate over, y equals 3 to y equals 6. So let's draw this region. There's y equals 3, y equals 6. The curves we're given was u of y equals the square root of y. So x equals the square root of y. And the other curve given, v of y equals 1 over y. So x equals 1 over y. And if I draw these, when y equals 3, I'll do the first curve. When y equals 3, x is the square root of 3. At that point. And when y equals 6, x equals, the square root of 6. A little bigger than that. That's between 1 and 2. This would be between 2 and 3. And that's, just part of it. This is just like y equals x squared, right? If I square both sides. So it's part of the parabola y equals x squared, just doing this, right? Up like that. All right. Then when I do x equals 1 over y, right, when y equals 3, x is a third. Square root of 3 is about 1.7. So let's put a third here. So you got that point, 1/3 comma 3 on this. And then when when y equals 6, x is even smaller, right? 1/6. And then you got this part of that curve, right? And then we're doing just between y equals 3 and y equals 6, right? So this region here. And it's being rotated around the y-axis to create some three-dimensional shape, with a gap in it, right? Because there's a gap between this shape and the y-axis, so there's going to be a shape with this big gaping hole in it, cavity. As before, if I want to create a disc, right, or a washer, I make a little thin rectangle here, a thin slice of the region perpendicular to the line I'm rotating around. Right? So it's got a horizontal slice, and every horizontal slice will correspond to some y value. And we'll say the thickness of this rectangle is dy. And when I rotate this rectangle, this thin slice around the y-axis, we create another washer, right? Another, just a thin disk with another thin disk cut out of the middle. And down the center of the hole here would be the y-axis. All right, and the radii, right? You have your inner radius, you have your outer radius. And because my thickness is dy now, pardon me, because my thickness is dy, I want these in terms of y. So you can see on the picture here, this, right, the distance from the y-axis to the inner curve, the left curve, would be the inner radius, which would be the x-coordinate of this point on the left curve. But the x-coordinate of this point on the left curve is 1 over y in terms of y. So the inner radius is 1 over y. And then the outer radius, right, is the distance from the y-axis to this point on the end of the rectangle on the outer curve. And that would be the x-coordinate of that point, right, going left to right, x-coordinate. And the x-coordinate of a point on the outer curve is the square root of y. All right, so now that I have these radii, we could just do total volume right now, right? The total volume of the shape created rotating this region around the y-axis. I'd be making these washers, finding the volumes of these washers for every y value from 3 to 6, and then adding them up, right? So we're doing integral from 3 to 6 for the y. And then of the volumes of these washers, right? And the volume of a washer would be pi times the quantity, the outer radius squared, right? So that's square root of y squared, and I know that would just be y in a second, but then minus the inner radius squared, which is 1 over y squared, right? That whole quantity. And then times the thickness. So this is the area of the big circle minus the area of the little circle inside that's cut out, and then times the thickness dy. And this, right, this is what they want. That's all they want, is set up the integral that would find the volume of the shape created. So we have the square root of y squared for the outer radius squared minus 1 over y squared for the inner radius squared. You have times pi times dy, integral from 3 to 6. That is this third option here. Right. Again, they have the picture of the region. Rotate that region around the y-axis, and you can, if I move this around a bit, you can hopefully see that this is a shape with a hole in it, right? It's not a... You can see that red graph. I mean, it's a small hole because like 1/6 is a tiny amount of stuff, right? If I zoom in here, maybe you can see there'd be a little tiny hole in the top. There's a hole, right? You can see the red disc, the red washer. That's just one thin little slice. Okay. All right, so once again, we're asked to set up an integral where we're trying to find the volume of the solid created by rotating some region around the y-axis. All right, so I'll graph this region once again. So between y equals 1 and y equals 2, it said. All right, between y equals 1 and y equals 2. Let's say that's up there. Now the curves are given as functions of x. You have y equals x, f of x equals x. And the other curve we're given is g of x equals 2 square root of x. So y equals 2 square root of x. Now if I'm rotating around the y-axis and I'm doing these discs or washers, I'm going to have a thickness of dy. So I'm going to get things in terms of y. So y equals x is x equals y. same thing. And when I take this other curve and solve it for x, x would be, y squared over 4 divided by 2 and then square both sides. Right? So you're going to want to get things, if you're rotating around the y-axis and you're doing a disc or washer, you have a thickness of dy, you're going to want to get x in terms of y. If you're rotating around the x-axis and you want a disc or washer, it's going to have a thickness of dx. So you want to get, y in terms of x. Right, so y equals x would have the point 1, 1, 2, 2, and just be a straight line. So there's y equals x, and then x equals y squared over 4, or y equals 2 square root of x. When x equals 1, you got 2, square y equals 2. And 2 root 2 is the square root of 8. It's a little higher than that, right? 2 times the square root of 2 is a little higher than that. So when you plug in 2, you get 2 root 2 up here, and it's part of a square root function, right? So a little curvier, than in a straight line. So yeah, this well, actually I should bring this here, right? When y equals 1, x equals a quarter. Should have been going from y equals 1 to y equals 2. All right, so for that second curve up here, y equals 1, x equals 1/4. So you got 1/4, 1, and when y equals 2, right, you got x equals 1, so you got 1, 2, right? And so yeah, it's just this part of the curve. My apologies. So ignore this part, right? Scratch that off. So in this region here, right, from y equals 2 to y equals 1 here, y equals 1 to y equals 2, between these two curves, my apologies. All right, so that region there in the green, and we're rotating around the y-axis and creating these washers. So I'm going to do if I want to create a washer or a disc, right, take a cut, take a slice, thin little rectangle that's perpendicular to the line of revolution, which will correspond to some y value, and the thickness will be dy, right? And when I rotate this rectangle around the y-axis, I create this washer, right? Again, a thin disc with a little disc cut out of it. Thickness dy, and the inner radius would be this distance here, from the y-axis to the right to this point on the left curve. That's the x coordinate, right? Just to the right, that's the x coordinate of that point. But I want it in terms of y. On that curve, right, x is y squared over 4. So the inner radius is y squared over 4. And then the outer radius, right, is the distance from the y-axis to the point on the end of the rectangle on the right curve, which will be the x-coordinate of that point. But on that curve, the x-coordinate is the same as the y-coordinate, so it's y, right? In terms of y, it's y. Right, so the total volume, I'll just skip again to the total volume of this entire shape rotated around the 3D figure created. I'm doing this washer thing for every y value from 1 to 2. So I'm going to go from 1 to 2 of, and the volumes of these washers added up. And the volume of these washers would be, again, pi times, right, you got the area of the big circle. So pi times, outer radius squared, so just y squared, right, the outer radius squared. minus, and then the inner radius squared, pi times the inner radius squared, y squared over 4 squared. And this will give me the area of this, the face, right, the area of this ring, and then times the thickness, right, times dy. And just like the last example, right, the last few examples, this is all I want. All right, the setup of the integral. So that's looking like this last option here. Again, they have, a picture of the region, then rotate that, have you rotate that region around the y-axis to see this 3D shape, with a hole in it, right? You can see the little empty space, the white space there, the hole in it, and the red right there is a washer, just one thin little washer. So doing this again, volume of a solid of revolution using the washer method. Again, for functions of y. This time they actually want the volume. All right. So once again, draw the region. But I'll tell you this, it's, we're getting 2.5 hours into this video now. I'll draw the region. I'll draw the thin little rectangle. Then I'm just going to set up the integral. All right. I'll point out the inner radius, the outer radius of the washer without actually drawing the washer from here on out. Okay. You want to see more washers? Yeah. Go back to previous examples. All right. So the picture of this region. So the one curve we're given is, u of y. We're giving functions of y. So x equals 2y plus 1. U of y equals 2y plus 1. Then the other function is v of y equals y. So x equals y. And we're between y equals 1, they say, and y equals 3. All right, so this first curve, when y is 1, this is 3. All right, so you'd have 3 on the x, 1 on the y at that point. And when y is 3, x is 7. And it's just a straight line, right? These are both linear functions here. So there's that first curve. And then x equals y, right? When y equals 1, x equals 1. And when y equals 3, when y equals 3, x equals 3. So there's that curve, right? And so the region being discussed here is, again, between these two curves over the interval from 1 to 3 on the y-axis, between 1 and 3 on the y-axis. So there's the region that's being rotated. It's being rotated around the y-axis again. All right, so take a slice at some y value here from 1 to 3. Got a thin rectangle with a thickness of dy. The inner radius for the washer will be this distance, which is the x-coordinate of the point on the left curve, right? So the inner radius is the x-coordinate on this curve, which in this graph is just x equals y. Right? This was x equals y. The outer radius for the washer will be this distance, and that's, again, the x-coordinate of that point on the right of the rectangle on the right curve. And x is, in terms of y, 2y plus 1 on that curve. All right, so the volume of this shape that's created, I'm going to be doing this, right, this creating a washer, finding the volumes for every y value from 1 to 3. I'm integrating from y equals 1 to y equals 3. I'm going to pull the pi out, right, it's a constant multiple. Pi times, then you have your outer radius squared minus the inner radius squared, which is just y squared, and then times your thickness, right, dy. This pi times this, right, this is the volume of one washer, and we're adding them all up from 1 to 3. Okay, now this integral here I know is going to be a rational number because you have a polynomial here and rational limits and rational coefficients. So I'm just going to type that in. Go to Desmos with my definite integral already set up. This is from an earlier problem. We're doing the integral from 1 to 3. And, I can leave it as x, just replace y with x. So that's 2x plus 1 squared minus x squared, right? I just replaced y with x. Okay, so that's 44 integral. So this ends up being 44 pi. There was a pi there. So I'm going to enter that. So pi times 44, 44 pi cubic units would be the volume of that shape. Great. Again, you could have all, if I test you in class or whatever, right, you're gonna have to do that yourself, right? Not just enter it into some calculator. But like I said, this is over 2.5 hours now. I want to speed things up. So there's the region. See what we get when we, rotate this region across the y-axis, right? There you go. This shape here with the hole in it. Right? That's 3D shape. Little saucer with a hole in it. All right. Okay, so another one, we're finding the volume of a thing where we're rotating around the y-axis yet again. So just like last time, I'm going to just draw the region, set up the integral, and if it's something I can do in Desmos, if it's something that's going to be rational, I'll put it in Desmos. All right. So this region here, one curve we're given is y equals x squared divided by 4, and the other curve, y equals 2x. Now, if I solve for x in these, here, x could be positive 2 root y, 2 root y, or negative 2 root y, right? Multiply by 4 and have plus or minus the square root. So we'll see which one actually makes sense for us to use when we go to plot points. And we're in it said the regions in the first bounded by these curves in the first quadrant between y equals 2 and y equals 3. We're rotating the region around the y-axis. Right. So this first curve, now when y equals 2, notice if they want me in the first quadrant, I need positive x values, right? So I'm not going to use this negative one then. That wouldn't make any sense. So it's this curve, x equals 2 root y. So 2 root 2 for the x, and y is 2, and 2 root 3, which would be bigger than that, for the x when y is 3. And it's part of some parabola, right? Y equals x squared over 4. So parabola opening up, and so like curve like that maybe. There's the first curve. And then y equals 2x, that's the same thing as x equals, half y, or y over 2. And when y is 2, x will be 1, should be less than 2 root 2. And when y is 3, x will be 3 halves. 3 halves. That'd be 2 root 2 is the square root of 8. 3 halves is the square root of 2.25. So yeah, that's less than that for 3 halves. All right, and I get this piece of this line. It's a line. All right. And so the region being described here is this region, right, between y equals 2 and y equals 3, between these two curves. And we're rotating around the y-axis yet again. So I take a slice, if I'm making discs and washers, right, I'm making washers here. Take a horizontal slice, right, perpendicular to the y-axis. Create a thin little rectangle here. Thickness is dy. Then for the washer, right, the inner radius will be the distance from the line to the left curve. And, the inner radius, that's just the x coordinate to that left curve, right, going to the right. And the x coordinate in terms of y on that left curve is half of y. So the inner radius in terms of y is half of y, and then the outer radius is this distance, right? The distance from the line to the right curve on that thin rectangle. That'd be the outer radius. And that's, again, the x coordinate of the point on that right curve, the right end. But in terms of y, that's 2 square root of y. All right, so the total volume of the entire shape that would be created by rotating this region around the y-axis. I'll be doing this for every y value from 2 to 3. Right? So I got the integral from 2 to 3 of the volumes of these washers, which is going to have pi times, so I'll pull the pi out, times, and then the quantity, your outer radius squared. Now if I square the outer radius, that's just going to be 4y minus, and then the inner radius squared is a quarter, y squared over 4, or a quarter y squared, and then times the thickness, right, dy. And once again, this integral here is another polynomial with, rational limits and rational coefficients. So I know it's going to be rational, so I'm just going to enter that into Desmos. You can do it yourself. It shouldn't take that long, and I'm just going to keep, well, let me change them to y now, I guess. But you can keep x, keep y. Right, replace x with y, or just keep y. We're integrating from 2 to 3 now, right? The limits are 2 to 3. And the integral we're doing is 4y minus y squared over 4, like that, right? So 101/12 times pi, 101/12 times pi, right? So I'm going to enter this as 101 pi in the numerator, all over 12, right? Cubic units for the volume of the shape created. I run you through it here, show you the region, show you what happens when you rotate that region around the y-axis, right? You start creating this 3D shape. You can move the graph around, right, and see what it looks like. Zoom in, zoom out. And we've got the volume. So this one we're rotating around the x-axis. Okay, so I'm gonna take vertical rectangles, have thickness of dx. I want things y's in terms of x's instead of x's in terms of y's. So once again, real quick sketch of the region, and then I'll draw a thin rectangle, make a slice perpendicular to the line of rotation, and then just set up the integral that would give me the entire volume. So one curve is y equals e to the half x, right? E to the x over 2. And then the other curve is y equals e to the negative half x, which is it's the same curve, just reflected across the y-axis, right? X becomes opposite. But we're between strictly 0 and 1 on the x-axis. They say between 0 and 1. All right, and then we're rotating around the x-axis after we're done. Right, I'll put that little loop there. Right. So for both of these, you have the point 0, 1. All right, when e to the 0 is 1. But then, e to the half, square root of e would be bigger than 1. So here's that curve. Right, that's this curve here, right, in orange. And then e to the negative half, right, when that's 1 over the square root of e, that'd be less than 1. E to the negative half would be down here when x equals 1, and I'll make this like a green curve or something. That's this curve here. And then the region we're talking about, is between these two curves over the interval from 0 to 1. There we go, right? And we're rotating around the x-axis. Right, so if I wanted to create one of those washers, I'd, pick some x value here, make a little slice with a thickness of dx. And then when I make the washer, right, the inner radius would be this distance. The outer radius would be this distance. The outer radius, that's just the y coordinate of that top curve, and I want it in terms of x. Top curve is this e to the x over 2. The inner radius is the y coordinate to the bottom curve, which in terms of x is e to the negative x over 2, or the negative half x. All right. So the total volume, when I rotate this region around the x-axis, get a 3D shape, right? I'd be doing this washer stuff for every x value from 0 to 1, and then adding them up, right? So we're integrating from x equals 0 to 1 of, the volumes of these washers, which would be pi times the outer radius squared, which would just be e to the x, minus the inner radius squared, right, would just be e to the negative x, and then times the thickness, right, dx. This won't be a rational number, right, so I can't do this. They want exact answers here, so I'm not going to do this one in Desmo, so I'll actually do it by hand. Pi times, integral of e to the x would be e to the x, and then e to the negative x, the antiderivative would be, negative e to the negative x, so this would be plus e to the negative x. And then we're going from x equals 0 to x equals 1. So this is pi times, and then, when you plug in 1, you got e plus e to the negative 1, right, minus, and then when you plug in 0, 1 plus 1, you got 2. And there you go. I'll just type that in without the parentheses here, around the e plus e to the negative 1. But there you go. That's the volume of the shape created. I times the quantity e plus, 1 over e, or e to the negative first, and then minus 2. Volume I times the quantity e plus 1 over e minus 2 cubic units. Great. Picture the region, rotate the region, see the 3D shape being created when you rotate around the x-axis. Move the graph around, play around with it, see that shape. We got the volume of it. Once again, around the x-axis. So I'll draw the region once again and just pick out a thin little rectangle that's, perpendicular to the line of rotation and find the volume using this washer method. So the curves given this time are just y equals x, f of x equals x, and g of x equals, or y equals x to the 3 halves. And between x equals 0 and x equals 1 and the x-axis, rotating around the x-axis again. All right, so 0, 0, 1, 1 will be on both of these. Now y equals x is a straight up line. Now numbers between 0 and 1, right, like a half or a third or 2/3, whatever, numbers between 0 and 1, when you raise them, the power is higher than 1, like 3 halves is higher than 1. They get smaller, right? Like 1/2 squared is a quarter. A quarter is smaller than a half. 1/2 cubed is an eighth. An eighth is smaller than a half. When you raise a number between 0 and 1 to a power greater than 1, you get smaller. So this x to the 3/2 power is going to be coming under. It's going to have smaller outputs than y equals x in this region between 0 and 1. So here's the region we're talking about. Right, and again, this is getting rotated around the x-axis. So I pick some x value in here between 0 and 1, create a little thin slice, a little thin rectangle with a thickness of dx. The inner radius in terms of x would be the y-coordinate of this bottom curve, y-coordinate of the point on the rectangle on the bottom curve, and that would be the x to the 3/2 power. And then the outer radius is the y-coordinate to the top curve, which is just in terms of x. All right, so the total volume, when I rotate this shape around the x-axis and create a 3D figure, will be the integral from 0 to 1, right? I'm doing this for every x value, from 0 to 1. Integral from 0 to 1 of, pi, the volumes of the washers created. Pi times, the quantity, outer radius squared, so just x squared, minus the inner radius squared, x to the 3/2 squared would just be x cubed, and then times the thickness. All right, and this one ain't so bad. I know this will be rational, but this will be pi times basically just 1/3 minus a fourth. Because when I plug in 1, I'll just get a third minus a fourth, and when I plug in 0, I'll get 0. So 1/3 minus 1/4. This will be 4/12 minus 3/12. That's pi over 12. All right, 1/12 pi cubic units. All right, it's pi over 12 for the volume. 5 over 12. All right, and again, you probably get a picture of the region, right? There's, zoom in, there's that thin region I talked about, right? Rotate it around the x-axis. Maybe we can see the shape being formed in this angle. We see the shape being formed, the 3D figure, and got got washers and stuff, the little red washers, and yeah. All right, keep moving. We're getting there. We're getting there. Another one. Again, I'm rotating around the x-axis. Find the volume. All right. So these are some lines. Once again, I'll just draw the region, do a little thin rectangle, and imagine a washer being created after the rotation. So the curves given to me this time are y equals 2x plus 1 and y equals 1. And we're between x equals 1 and x equals 2 and rotating around the x-axis. So between x equals 1 and x equals 2, we're going to rotate our region around the x-axis. All right, now first curve, when I plug in 1 for x, I get 3 for y. And when I plug in 2 for x, I get 5 for y, right? So that's just a line. Right, so there's this curve, right? And then the other curve is just y equals 1, no matter what. So it's 1 on both ends, right? You got a horizontal piece of a horizontal line. So the region being talked about is this region here over the interval from x equals 1 to x equals 2, right? That's our region. All right, then I'm taking slices perpendicular to the x-axis here. For any x value between 1 and 2 here, creating this little thin rectangle with a thickness of dx. The inner radius is always 1, right? That distance from the x-axis to the bottom curve is always 1. And the outer radius is the y-coordinate to the top curve, but the y-coordinate on the top curve in terms of x is 2x plus 1. Sorry, that says 2x plus 1. So when I rotate this region around, integrate from 1 to 2, right, the volume of this whole region, this whole 3D shape that would be created, so the volume of the solid, the integral from 1 to 2 pi times, this is the volume of each washer. pi times, the quantity, the outer radius, which was that 2x plus 1 squared, then minus, the inner radius squared, 1 squared, which is just 1, right? So really, just write 1, then times the thickness, right? And this expression here would be 4x squared plus 4x, and then plus 1 minus 1. So this is 4x squared plus 4x. So I'm going to, because this is a nice easy polynomial, and again, I'll just go to Desmos real quick, get what this value is, right? So we have the integral from 1 to 2, 4, 4x squared plus 4 squared, this, plus 4x, sorry, plus 4x, and then dx, right, dx. 46 thirds, right? The value of that integral is 46 thirds, and don't forget the times pi. So 46 pi over 3 would be the volume of the solid created here, 46 pi over 3. Great, almost done. So you got the region again, rotate it around the x-axis, see the 3D shape being created here with the hole in it and the red slice, red washer. Right. So yeah, so this time rotating my region around the y-axis. And yeah, so again, I'm going to draw the region, make a washer, draw a thin little rectangle that would create a washer, right, when I rotate it around the y-axis, and then set up the integral for the volume of the whole solid. So we're between y, they say between y equals 1 and y equals 3. And the curves we're given are, u of y or x equals y to the 3 halves plus 1. And the other curve is v of y or x equals y. Now x equals y is no problem, right? When y is 1, x is 1. When y is 3, x is 3. So that's a straight line. That's that curve. And then the first curve I got there, when y is 1, x is 2, right? 1 to some power plus 1, say to this point. And when y is 3, 3 to the 3 halves, 3 to the 1.5. That'd be 3 times the square root of 3, so about 5.1, and then plus 1, so about 6.1, but I'll just say 3 to the 3 halves, x is 3 to the 3 halves plus 1, be out here somewhere. And then they're connected. Now, it's not going to be a line. I think it'll be more of a curvy shape. Now let's do this curve. It might curve the other way. I don't really care right now. I just know that it's to the right of my first curve. Oops, I should have did that in a different color. That's that curve there. And so the region here between 1 and 3 is this region. And we're rotating around the y-axis. So let me pick a value of y here between 1 and 3, create a thin little slice, thin little rectangle with a thickness of dy. All right, and then your inner radius for the washer, right? When I make a washer by sweeping this rectangle around the y-axis, the inner radius will be the x-coordinate of this left point, this left curve, the x-coordinate of the left point rectangle. With that left point, the x is just y, x equals y on that. And then the outer radius for the washer would be from the y-axis to this right point on the rectangle, which is on the right curve, and that x-coordinate is y to the 3 halves plus 1. Okay, so set up my integral now. The volume of the solid created Total volume, I'd be doing this washer thing for every y coordinate from 1 to 3. So integral from 1 to 3. And the volume of each washer would be pi times, pull the pi out, then the outer radius, right, this y to the 3 halves plus 1 squared, minus, and then the inner radius squared, which is y, right, y squared, and then times the thickness, right, times dy. Now this won't be a nice rational number, and they do ask us for an exact answer here, so I'm going to have to do this by hand. So multiplying this out, we have pi times the integral from 1 to 3 of squaring this will give me y cubed plus 2 times y to the 3 halves plus 1, and then you got the minus y squared over here. Right, so 4 terms in this expression. And then I'm anti-differentiating and evaluating at 3, evaluating at 1, and subtracting. Right, so pi times 1/4 y to the 4th, and then this would be y, right, y to the 5 halves, then times 2/5. So then times the 2 out here, that'd be 4/5 y to the 5 halves, plus the antiderivative of 1 is y, minus antiderivative of y squared would be 1/3 y cubed. Right, and then we're going from, y equals 1 to y equals 3. Right, I'll plug in 3, plug in 1, we'll subtract the values. This is going to be pi times, and then the value of this at 3. Okay, so 3 to the 4th, 81. So 81/4 plus, now 3 to the 5 halves is just 3 to the 5 halves. I mean, you could say it was 9 times the square root of 3 as well. So yeah, maybe I'll do that. So 3 to the 5 halves, that's 9 times the square root of 3. This would be 3 squared times 3 to the half. So 9 times 4/5, right, that's 36/5, right? So plus 36/5 times the square root of 3, then plus 3, then minus 1/3 of 3 cubed, right? 1/3 of 27, yeah, minus 9. So that's the value at 3. Then I'm taking away the value at 1, which is just, everything is got just a coefficient here, minus 1/4. Then we'll subtract, 4/5. I got plus 4/5 here, and then plus 1 minus 1/3. All right. And if I were to distribute the negative here, I'm sure you can type this in, and it would give it to you, but I'm gonna do this. So we got pi times, now here I have 81/4 minus 1/4, that's 80/4, that's 20. The 3 minus 9 up here, that's -6. And then minus the 1, that'd be -7. All right, so I've taken care of that and that and that. And I've subtracted this and I've subtracted that. Uh, got the positive 36/5 times the square root of 3, right? That hasn't been touched. Got that in there now. And then minus, I didn't do the minus 4/5. I didn't, 4/5 minus 1/3. 3 over 3, that'd be 12/15. Minus 5 over 5, that'd be 5/15. 12 minus 5/15, that'd be 7/15. We'd have minus 7/15. And then 20 minus 7 is 13. if I think of this as 13 over 1, right, times 15 over 15 to get a common denominator with the other fraction. This would be 195, right? 130 plus 65, 195 fifteenths minus 7 fifteenths, 188 fifteenths. And that's as simplified as I get. So we get this, we get pi times the quantity, 188 fifteenths plus 36 fifths times the square root of 3. And that'll be the volume. Now you could, I'm pretty sure though, you could have typed it out the way I had it earlier and it'll still give it to you, right? As long as it's equal to the final result. So let me enter that. I got pi times the quantity, 188 fifteenths plus 36 fifths times the square root of 3. I'll close the parentheses there. That's the volume of the shape created. Great. Again, they have the picture of the region. They have you rotate it around the y-axis, see the 3D shape being formed, right? And we got the volume. So here we go again, but this time, right, this time we're rotating around a different vertical line, right? Not around the y-axis, but around the line x equals 1. So that's going to change a little bit. All that's really going to do is add 1 or subtract 1 from the way I normally calculate the radius, the inner radius and outer radius. Right? That's all it's going to do is shove those radii 1 unit more, 1 unit less, depending on where the region is. All right, so I will once again graph this region. So XY axis. All right, the two curves given. Got functions of y. All right, so u of y, that's same as x equals and 1 minus 2y. The other curve is v of y, so some x coordinate equals y squared plus 1. And we're going between y equals -2 and y equals 0 only. Okay. And we're going to rotate around the line x equals 1. So I'll draw that line up later. All right, so the first curve, when y equals -2, x is going to be 5. All right, let's put 5 here, 5 for x, -2 for y. And when y equals 0, x equals 1. So you have 1, 0. And that's just a linear, right? So it's a straight line curve there. So that's that curve. And then x equals y squared plus 1 is just a parabola, opening to the right. And when y equals 0, x equals 1 again. Right? When y equals -2, x equals 5 again. But it would be a parabola, right? The values between 0 and -2, like when I plug in, say, -1 for y, this would be x equals 2. Here it would be 3, so it would be to the left. Right, it's part of this parabola opening to the right here. Right, that's to the left. It's to the left of that curve on the right there, the left of the line. Right, so there's the region talked about between y equals 0 and y equals -2. But this time, right, we're rotating around the line x equals 1. Right, so I'm gonna make that a dotted line here. Right? So here's the line x equals 1, right? It's a vertical line. There, rotating around that line, not the y-axis. So what that's going to do is it's going to take my normal radius, right? The normal radius we found was from the y-axis, and I'm going to subtract 1 from that, right? It's going to make it one less. The distance is 1 unit less, right? Because can you see when I take a slice perpendicular, pick some y coordinate between 0 and -2, create a thin little slice here in the region. It's got a thickness of dy. and then the inner radius is here, right? Just from the line x equals 1 to this inner curve. Well, that's this x coordinate minus 1, right? Again, it's just 1 less than our usual radius from previous examples. So what is the x coordinate on that left curve? That's y squared plus 1. I'm subtracting 1. So that inner radius is just y squared. Right? It's y squared plus 1, then minus 1. And then the outer radius is the distance from this line to the outer, the right point on the rectangle, outer radius. Again, it's our usual x coordinate for that point, but then minus 1, right? It's 1 less of a distance, 1 less of a unit distance. So that'd be 1 minus 2y to the outer curve, but then minus 1, so it's negative 2y. All right, get rid of the 1. And this would be positive here because our y coordinate, this is a positive radius because our y coordinates down here are negative. So negative times negative, this is representing a positive number. All right, and then I do this for every y coordinate from negative 2 to 0, right? Go low to high. So then the total volume, right? My integral for the volume, the integral from negative 2 to 0, pardon me, of the volumes of these washers that would be created when I rotate this little rectangle around the line x equals 1. Pi times, our outer radius squared, which I said was negative 2y squared, minus the inner radius squared, which we said was just y squared, right? Times the thickness dy. And this is just going to be a polynomial. So I'm just going to type this in and then multiply it by pi. So if I know it's a polynomial, it'll be a rational number when I integrate it, right? All the limits of integration and all the coefficients are rational. So we're integrating from negative 2 to 0. Of, let's just get rid of this here. So we had the, negative 2y to the second power before y squared. And then y squared squared is y to the fourth. So minus y to the fourth. And then with respect to y, all right, so 64/15 times pi, all right? So 64 pi over 15 would be the volume of the 3D shape created. 64 pi over 15. Double checking, 64/15. Yes, yes, yes. Great. All right, so there's one more objective to finish up here. And it's all the same, though. It's still this washer stuff and rotating a region around some line. All right. Again, there's your region. You can create the 3D shape, rotate it around see that region moving around the line x equals 1 to create this like little cone looking thing. But it's not really a cone because it's got like a part of it hollowed out. I don't know if you can see that, but part of it would be like it's got a divot. It's like a bundt cake. It's got a divot in it. Anyway, we got the volume. All right, so last objective, which we're about a quarter of the way through, so almost there, right? The mastery bar is at 85%. So this is same stuff. But this time, remember, if I'm not rotating around the y-axis, I'm rotating around some other vertical line, x equals 5. And all it's going to change is it's going to add 5 or subtract 5 from the normal way I find the radius, the outer radius and inner radius for those washers. So same thing, I'm going to draw the region being described. So we're going from, say first quadrant between y equals 2 and y equals 4. So I want things where, I want x in terms of y here. I'm going to be integrating with respect to y when I make washers or disks. So the first curve we're given is y equals x, which is the same thing as x equals y. The other curve is y, g of x equals 2 square root of x. But that's the same thing as x equals y squared over 4. Divide by 2 and square both sides. We've seen a curve like that already. say y equals x, when y equals 2, x equals 2, when y equals 4, x equals 4, right? And this is just a straight line. So there's that curve, and the other curve, right, when y equals 2, x equals 1, right, when y equals 2 is 4 over 4, x equals 1, so you get the point 1, 2, and when y equals 4, 4 squared over 4 would be 4, right? So 4, 4 is also on that curve, and it's part of a parabola, right? It's like a parabola shape opening to the right, so there's that curve, right? And then between, y equals 2 and y equals 4, so this region here. And we're rotating this region around x equals 5, right? So I'll make a little dotted line here, vertical line. Here's x equals 5, and we're rotating this region around that line. So I make a little slice, right? I'm going to take a y value here between 2 and 4, showing a slice, perpendicular to the line we're rotating around. And then this little rectangle, when I rotate it around the line x equals 5, I'll create a washer. Thickness of that washer I'll call dy. Now the inner radius is this, right? The distance from the line to the innermost curve, the curve closest to it. So that is a little different than before, right? If I'm going from normally I would go from the y-axis. So the distance from the y-axis to this line is 5. And then the distance here, from here to the inner curve, that's the x value of the inner curve. I'll call it xi or x1. So this distance here is 5 minus that, right? It's 5 units, the whole distance from from the y-axis to x equals 5, minus this distance from the y-axis to the right curve. And then what is x, this x coordinate of the point on this line? This is y. So 5 minus y is the inner radius. And then similarly for the outer radius of the washer, right, it would be the distance from the line we're rotating around to the curve furthest from it, outer radius. And again, it's the same thing. It'll be this distance here is the x coordinate to the this outer curve, and so this outer radius I'm looking for here, the distance from the line we're rotating around to this point here, is 5 minus that x coordinate. That x coordinate, we said, is the y coordinate squared divided by 4, right? If we're on that curve. So the outer radius is 5 minus y squared over 4. So the total volume of this shape, be the integral. I'd be doing this for every y coordinate from 2 to 4 of the volumes of the washers created by rotating this little rectangle around the line x equals 5. So be pi times, and then your quantity, the outer radius squared, right from here to this left curve, which we said was 5 minus, y squared over 4 squared. That's the outer radius squared. Then minus, and then the inner radius squared, right, the distance from the line we're rotating around to this right curve. It'd be 5 minus y squared, and then all that, with respect to y times the thickness dy. Once again, this is a nice polynomial, and I've got rational coefficients, rational limits of integration, so I'm going to just enter this into Desmos and multiply it by pi. So we're integrating from positive 2 to positive 4 of 5 minus y squared over 4 squared, then minus 5, the quantity 5 minus y squared. Right, so that's 106 15ths times pi, right? So 106 pi over 15. I'm just double checking to make sure I typed everything correct. Right? So 106 pi over 15 for the volume of the shape created there. Wonderful. And again, they probably show you, picture of the region. And then what happens when we rotate this region around x equals 5, right? So the purple dotted line here is x equals 5. See the rotation around that, right? You get that shape, this 3D shape here with the hole in it. And it'll be a three-dimensional figure, and we found the volume. So probably just the one more. Looks like I'm almost there. So this is another one where I'm rotating around a line that's not the y-axis, but some other vertical line, right? Rotating around x equals 2. So once again, I'll draw the region and do all the same stuff I've been doing the past several examples, right? All right, so I'll draw this region. Right, so the curves given are f of x equals 2x, right? Y equals 2x. But since I'm creating disks and washers and I'm rotating around a vertical line, I want x in terms of y here. So that curve is also the same as x equals y over 2. And then the other curve is like the previous example, y equals 2 root x, or x equals y squared over 4. Right, divide by 2 and square both sides. We're just going from between y equals 1 and y equals 2. Now y equals half, x equals half y. So when y equals 1, x equals a half. Right, so the half there. And when y equals 2, x equals 1. So you got 1, 2 on that line. And it's just a line. So that's that curve. The other one's like a little like square root function or half a parabola opening to the right. When y equals 1, x equals a quarter, which is less than a half. So quarter 1. And when y equals 2, x equals 1, so you got the point 1, 2 again. And it's just as part of a parabola opening this way, right? And then we're just talking about the area between y equals 1 and y equals 2, so that region there. And this is being rotated around the line x equals 2. So very much like the last example, where the line we're rotating around is to the right of the region. There's x equals 2, this vertical line, we're rotating around that. Okay, so I take the slice perpendicular to this, right? So for some y coordinate, think about some thin rectangle in here with a thickness of dy. If I rotated that around the line x equals 2, I'd create a washer. The inner radius would be this distance, right? The outer radius, this distance for the washer. And the inner radius, right, would be 2, then minus the x coordinate of this point on the right here. 2 minus this distance here between my finger and the pen. So it'd be 2 minus, and then the x coordinate of this point on the right we said was y over 2. And then the outer radius, again, is 2 minus the x coordinate of this point on the left of the rectangle, right? 2 minus this x coordinate. And this x coordinate would be y squared over 4, right? So 2 minus y squared over 4. All right. And again, the same setup. So if I do this for every y value, create these washers for every y value from 1 to 2, right? The total volume is, the integral from 1 to 2 of the volumes of these washers, which would be pi times quantity, outer radius squared. So this was what we said the outer radius was. 2 minus, y squared over 4 squared minus the inner radius, which we said this squared. 2 minus half of y squared, and then times the thickness, right, times dy. And once again, this is going to be a nice polynomial, so I'm just going to enter this in Desmos to get a rational number and then multiply it by pi. It's not too dissimilar from the last one, right? Instead of 5 minus y squared over 4, it was 2 minus y squared over 4. And instead of 5 minus y, it was 2 minus, half of y, or y over 2. And the limits of integration were from 1 to 2. All right, so 1 to 2. Right, so it's 113 240ths times pi. And again, just double checking to make sure I typed everything correctly. Yes, all right, so 113 pi over 240. So that'd be the volume of the shape created. Over 13 pi over 240, 240. That should be good. Great. And that should be it for the assignment. All right, once again, you got the region there that we drew. Rotate around the line, x equals 2, right? This little purple dotted line here is x equals 2. And, again, you can see what happens when I rotate and create that three-dimensional shape. And we got the volume of it down here. Right? And that is it. Right. So just like I said at the top of the video, right, the questions I saw in this are not going to be exactly the same, or the numbers might be a little different, or the curves might be a little different, but as the ones you'll see when you work on your own. But the all the objectives are the same, right? The types of questions you'll see are exactly the same, and the way you go about doing them are exactly the same. So hopefully watching me do these here help you out when you're working on them on your own. Okay. And thank you very much for watching.